In this lesson, we will take a look how we can prepare our own characters for the use in the Houdini crowd system. So first, let's make sure that our project is set up correctly. Under aliases and variables, let's see that the $job variable is set to our project files folder. If not, just select File, Set Project, and point it to the project files folder. Okay, so here's already created the mocap biped 1. This is a node provided by Side Effects, and it's an animated character which you can use in crowd systems, but we will use our own character. So to do this, we first need to import our character as an FBX file. Under Import, Filmbox FBX, just take a look in the referenced files, in the job referenced files, you will find in the FBX folder the T-Post Soldier FBX. That's the one that we need. And here are quite a few options. For now, you can just leave everything like it is. Just a small hint. If you are going to load many FBX files in one Houdini scene, sometimes it's good to check these two checkboxes here, because if you let them like this, so the files are not unlocked, then Houdini will save all the contents of the FBX file, like animation data, skinning, will save it into your Houdini file, so the file can get pretty huge. But for now it's fine like this, so select merge, not import. Import will create a new scene, just select merge. And here is our soldier. Pretty big, but we will change the scaling later. All the nodes are into the subnet, so let's dive in and take a look. Here you can see the bones, the null objects with all the transformation data on them, some pre-set up materials, and this is a geo container. In there you will find the skinning. Skin from the FBX file is applied here. So painted skin weights in Maya or in any other applications will be loaded fine. Another thing, if you want to group something here or assign a material inside here, it's important to do it between this and that node, not down here. Because if we bake our agents, the nodes which are behind this mesh deform will be ignored. So put any modifications or nodes here. Also important, name your geocontainers properly, because we can use the material style sheets overrides later on in the crowd system to add some variations to the textures or the colors of a character. And for these modifications, we need the exact name, so it's important to name them properly. We will also create another geocontainer for the weapon and load them. It's an OBJ, so the file node is fine. Just select in the referenced files, select OBJ and then M16 OBJ. It's also in this huge scale. Let's scale this one down really fast. Just drop a transform node, scale 0.1, okay. At the moment it's not in the right position, but we will take care of that later. The pre-setup materials is just a blend shader that we don't want, so delete this one and drop down 2 mantra surface materials, one for the soldier and the other one for the weapon. Okay, for the soldier we also have a texture map, so check this use map checkbox and load the texture. It's in the reference files in the texture folder, soldier diffuse PNG. And perhaps let's put here the base color bit 0.5, and for the weapon we just select a dark color. Okay, so now we need to assign the materials. Here on top you can, in the material tab, just select your created material. It's in this case a soldier. It's important that you have this export relative path checked down here. If not, there will be problems later on in the crowd system. And for the weapon as well. Okay. Now let's hit this here, then display the materials in the viewport. You can see everything is assigned properly. Okay, perfect. So at the moment this is just a subnet, but the idea is also to create, like this one here, a digital asset out of it. I think the advantage of this workflow is that we have our base character that we can set up properly, assign all the materials, make sure the geometry is fine, and then we will only load FBX files with just the skeleton and the animation data and transfer this animation data onto our prepared character. So you don't have to prepare every FBX file again, just prepare it once, this digital asset, and then we can apply the animation data. So how to do it? Let's make first a digital asset out of this subnet. Right click, create digital asset. Let's name it soldier. Okay. And save it also to the reference files, and they find an OTL ordner and there select soldier. Okay, accept. So now there's a pop-up with all the settings of a digital asset. For the moment, you just have to look at here, save, and deselect this check for external references, because otherwise there will pop up some error messages. I hit accept, and now our subnet is a Houdini digital asset. Let's dive in and let's take care of the scale problem. Just drop in a null, connect it, 0.01, and now you can see that our character is in the right scale, like the mocap biped one. Okay, to transfer an animation, first we need one. So let's import another FBX file. In the same folder you find the idle rifle 01 FBX, just import it, merge it into your current scene, and if we focus on this one, you see it's just a skeleton with animation data. So pretty lightweight. So how do we get it onto our T-pose character? For this, we going to create a ChopNet inside here, which can deal with animation data. And inside there, we create a fetch node. With this node, we are able to fetch the animation data from the skeleton and apply it to our character. So to have a bit easier later on, we are going to expose or promote these settings here, from which node we want to fetch it and so on, to the top level of our digital asset. So there's not even the need to dive into our asset to change the FBX from which we are fetching our data. You can just fetch it here on top. So to do this, again, we have to modify the type properties of our asset. So type properties, and in this case under parameters, we see the transform and subnet parameters. We don't need them, so just hide them for the moment, invisible. And to expose these fetch parameters here on top, we don't need to create all the parameters and link them. You can just go here from nodes, search for your shopnet, fetch one, and then drop in here the source settings. Okay, hit accept, and now you will see that everything is on top here. So we are going to fetch the idle rifle 1 animation, and at the moment it's just getting this top node, but we want all the nodes inside, so another slash and an asterisk sign to get all the bone transformation data. But we just want the translation and rotation channels, but all of them X, Y, and Z. So asterisk sign again and say just created channels. So, but our character is still in the T-pose. That's why we are not exporting the data to our character. So dive into the ChopNet. Make sure that here is the sample rate is at 30 sampled, because the scene is at 30 frames per second. Also the animation data. And Here you can set the export level or context. So at the moment it would be exported here into this shopnet 1, but there are no other nodes. So we have to export it one level higher. So just like this. And here you have to hit this little export flag. And now, as you can see, our character is moving. Perfect. These settings also have to be set once. Now, in the future, we only have to modify this file from which it fetches the animation data. So last but not least, the weapon is not moving with our character. So let's dive in and parent this weapon to the right hand bone. Let's see where it is. Here it is. Right hand. Just make sure that the keep position when parenting checkbox here is on. It's the same with maintain offset in Maya when constraining. And then just connect it to our soldier right hand null, and you will see it moves correctly. Okay. The last step would be to save our digital asset so we can also use it in another scene. So say save node type. Okay, so we are ready for now. In the next lesson, we will take a look how we can bake out the different animations as agent clips. Welcome to the third lesson of the Houdini 15 crowd tutorial. Now we will take a look how we can write out our soldier here as an agent for the crowd system. As you can see, I imported a few more animations here, so it's the best to start with the scene file from this lesson. Here we have the digital asset of our soldier. Now let's jump to the out context to write it out as an agent. To do this, create an agent node, and let's name this one soldier 1. And as a source, we pick our object subnet, so our digital assets, the T-pose soldier here. Okay, minimal nodes is checked, and that's fine because this toggle just makes sure that only the visible geometry nodes inside your agent subnet gets written in the agent definition. If you have some invisible nodes that you want to be in the agent definition, make sure you deselect this toggle here. Houdini will automatically create a collision layer for our agent. That's fine and it's a good starting point, but in the future we will also modify this collision layer to work better with the ragdoll effects. The clip name is really important. In this case we put idle 1 or just idle because it's the idle animation, and always make sure you use a unique name here because with this clip name we have to invoke the animation later on in the crowd simulation. Our animation is already in place. That means that our agent walks, shoots, runs all on the spot. But if you have an animation where your character is walking through world space in the animation, you have to check convert to in-place animation and select a locomotion node. Then this will subtract the world space motion before it writes out the animation for the agent. Because all agent animations have to be in place animations. Okay, our agent name is soldier1, and it gets written out to the cache directory in a subfolder with the agent name, soldier1. Houdini writes out 4 different files for our agent: the rig, the layers, a shape library, and the clips. As this is the first soldier one we write out, it's fine like it is. But for the next ones, when the first one is written out, we can deselect the 3 toggles here because all animations will share the rig, the layers, and the shape library. So, but for the first one, just keep them checked. And last thing we have to set is the frame range. So we break the connection here. Take a look on our subnet of the length parameter, copy, and paste a copied relative reference here. So we will always make sure that the range we write out is corresponding to the animation range. Okay, now we are ready to write out our first agent. Save to disk. Takes a few moments, and now we have written out our first agent. Perfect. Okay, I created a few more agent nodes down here to write out the additional animations. If you want, you can continue writing them out, or you just use the ones in the reference file folder for the next lessons. If you want to write out more animations, just pick them in your digital asset here. For example, idle rifle shooting. Make sure it gets loaded properly. Okay, as you can see, our agent is shooting now. And just back to the out context, here's soldier idle shooting. Frame range is already set correctly. And as you can see, as I mentioned down here, just the clips checkbox is on. And we just say save to disk. Okay, next animation is saved. So I will continue writing them out. You can do so as well, or you just use the ones in the reference file folder. So see you in the next lesson. Welcome to the next lesson. Now we will set up our scene geometry for the crowd scene. In here I just placed a file node, and now we will start with the first geometry, which is the beach. So just pick it here in the job reference files folder. You will find in the bgeo folder the beach. So just load this one and you will see I prepared a piece of geometry here. Here will be the defenders of the beach, and from here the boats will arrive. Okay, very nice. The beach is here. And now we will create a null to create an out node for our beach to keep the scene very clean. Out beach. If you write it in capital letters, it will automatically appear in any list in Houdini in the first place. Okay, just out and give it a blue color so everything stays nice, clean, and organized. Okay, beach is here. So next would be the sea. So copy the file node and load in the sea, which is here. Okay, and down here we will create a merge to look at both geometries at the same time. Merge. Okay. As you can see here, here's the sea and here's the beach. The sea looks a bit boring, so we will use some built-in Houdini nodes to make it appear a bit more like a sea, which is the ocean evaluate and the ocean spectrum. Okay, in the elevate goes here the spectrum, here's a geo, and as you can see, tada, we have a nice sea. Just tweak it a bit, just bring the speed down so we have smaller waves and the grid size up so we don't have as many repetitions. Yeah, okay, and give everything a bluish color here. Okay, yeah, that looks more like a sea. Very nice. Okay, and also here we will create an out node so we can grab the beach later on for our boats. C. Okay. Very good. Next would be the placement of the sand barriers. I try to create this whole scene as procedural as possible. So later on, if we want to have more sand barriers or less, or more tank traps and so on, more boats, more arriving soldiers, everything will be procedural. So you can just tweak the number and everything will work. Okay, to place the sand barriers, we will use a paint node and paint the barriers onto our beach. I think that's a really nice way to place them, so we don't have to move them manually somewhere, just paint it black where you want to have the sand barriers. Okay, let's first assign a black color here, and now let's make the brush size perhaps a bit bigger. So let's paint where you want to have sand barriers, perhaps some here, here. You can place them wherever you want. Our crowd later on will avoid them and run around in the best case. Okay, some more here, and perhaps here. Okay, very good. So how do we get our sand barriers there now? For this, we will create a scatter SOP, and we don't need all the stuff here. Oh, that's a few too many points. Okay, just select here density attribute and the color, which is CD, and put the density scale to, let's say, 3. Okay, that's better. You don't need to use this relax function, just leave it like it's like this. And now we use a copy SOP to copy our sand barrier geometry, which we have to load as well. Just copy a file node and load the sand barrier here and copy it onto our beach. Okay, very nice. Just a few too many sand barriers. Okay, no problem. For this, we will use a fuse node and fuse the distance to, let's say, 4, and check this box here, keep unused points. Otherwise, it will just delete the points because there's no assigned geometry. And there it is. We can merge it also into here, and now we have an attribute mismatch down here. That's why it's appearing a bit strange. That's why here we have some normal, a vertex attribute, and on this geometry there's no normal. So we just put in 2 normal nodes, and now we have nice and clean geometry and nice placed sand barriers. Okay, also here we will create out sand barriers. Okay, perfect. So the last thing for our beach at the moment would be the tank traps. For this we use the same method. So again, a paint node. Yeah, paint node, just template this so you can see where our sand barriers are placed. And now you can paint here. Okay, black 1. And place now the tank traps where you want them to be. Okay, some here, some here. Okay, this tank traps our crowd later on will also avoid. A special thing about the sand barriers is our crowd will try to reach them and hide behind the sand barriers. Okay. Okay. Okay, perfect. Now, same procedure. We can just copy these nodes here because it will be the same process and put them here. Okay. Okay, now we will put the fuse radius to 3.5. Load our tank trap here, and it will be copied to the geometry. Okay. We can put them even closer to each other, so let's put here 1.5, and now we have a few more because the fuse radius is less, the distance in which the points get fused. Okay, that looks good. And yeah, that was the last thing for the space scene here. The next step now would be the boats. So we make them also procedurally placed, and then they will arrive and automatically open their front gate so the soldiers can jump out and start running. Okay, don't forget to put here out tank traps because we need to reference them in the crowd system later on as an obstacle. Tank traps. Okay, see you in the next lesson where we will prepare the boats. So let's continue with the next geometry here, which are the boats. Okay, so let's object merge our C into this geometry here, out C. Okay, perfect. As you can see, as I already mentioned, now all the stuff with uppercase is up here. You don't have to search it down here. Very nice. Into this object, so all transformations will get merged into it. Now we will use again a paint node to define the placement of our boats. Okay. Okay, perhaps a little bit bigger brush. Very nice. So perhaps here, 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 here. Yes. Okay. So about, let's say, 30 boats. Okay. Now we will drop down a scatter again and use force total count to 30 and use again this attribute here and do a relax iterations. Okay, so next a fuse node, because we don't want to have the boats too close to each other. Okay, so that looks good. About 12 boats at the moment. I think that's nice. And now we need a really procedural way to get these boats moving. Because I mean, we could also animate every boat with a transform, but I think there needs to be a better way in Houdini to do this. The idea is to add velocity to these points until they reach our beach here. Then the velocity will go down to 0 and our boat stop and the gate opens. So how can we do this? First, let's create some attributes with a point wrangle here. Drop it down, and we need two attributes. At first, the water attribute and the open attribute. So water will be the attribute how fast our boat is moving. So I think 0.18 is a good value, and at open will be 0 at first because it hasn't reached the beach. Okay, so now drop down a solver so we'll add every time step this value here until the boat reaches the beach. For this we for sure need the beach, so object merge it in here as well, our beach into this object, and for the beach we also create this attribute with a 0 value. And for open we will create 60 because we want to rotate it until 60 degrees later on the door of the boat. Okay, put it in the second input of the solver, and now in here we use an attribute transfer node to add this every time step. So we go down here, okay. And at first we just want the water attribute to be transferred. Okay, that's good. And let's say when it is 2 meters away, it will start transferring the 0 value to our boats of the water, of the speed of the boat. Okay, so drop down a point warp here. And now we will create the motion of the boats. So we need a vector to float for the position because we want to add this water value every time step to our position, to the position of our points, but just to the z position value. That's why we drop down the vector to float, so split it up into x, y, and z. And now we need a float to vector to merge it again into one and put it here. Okay, so first two values, just pipe them through, and to the last value we will add our attribute. So in this case it's the water, so use a bind node to import it. Bind. It's a float and it's called water. Okay, so put it here. Very nice. Okay, so now because it's in a solver, it will run every time step and add it to our boat's point position. Okay, let's see if it works like we want. Oh yeah, very nice. As you can see here, our points are moving. Let's, just because the geo is changing constantly, just drop down here a time shift to freeze the ocean to the first frame. Okay, very good. So as you can see here, our boat points are moving to the beach. Very good. Okay, now we want another attribute transfer to transfer the open value. And for this one, because we want to rotate it slowly, make sure you just choose open here, and so make it 2 meters and 2 meters blend, so it will smoothly open its gate when this open value is transferred. So for later we will create another attribute which is called landed, so we know when our soldiers needs to start moving. For this we use an if the at water is 0, then we set this landed attribute to 1, and this will be later on a trigger in the crowd system, because you can use every attribute here to trigger some actions in the crowd system later on. Okay, yeah, very good. And now drop down a trail node, because we need the velocity of these points which are moving also for our crowd agents to move accordingly. So in the trail, choose compute velocity. Yeah, that's nice. Okay. So if you look here, you can see we have a velocity attribute. Another point for the crowd system, as I said, we need the velocity. So we need to write it in a special attribute, which is a vector, and we call it vBoat, and set it to the velocity values x, y, and z. Okay, and last but not least, we need an ID to identify every boat. So a boat ID, which is just the PT num. So the point number. Okay. Very good. Yeah, now is the moment to create a copy node and exchange these points to real boats, which will look a lot nicer. So points in here, and a file node in which we will load our landing boat and copy it onto our points. Yeah, very nice. Now the landing boats will move with our points until they reach the beach. I hope so. Let's extend our frame range here. Later on we will need 1200. Okay. And again, let's see if our boats stop. Yeah, very nice. When they reach the beach, our boats stop. Okay, that's nice. So to spawn our crowds, we will use another copy with a much simpler geometry. Just create a grid with a size 7 by 7 and 2 rows and 2 columns. And now we need to transform the grid a bit to make it fit the boats. Let's see. Yeah, no, we need to transform it. So let's rotate it by 90 degrees here and just move it a bit. So our boats are a bit smaller, so let's 2.3. Yeah, that looks more like our boats. Okay, very nice. So now we need to create again some out nodes to get it easy into our crowd system later. Out boats. And here we will create an out render because we for sure want to render our nice boat. So you with control click you can set render flag, so we can display this one here to work with, but in the rendering it will always render the one with the render flag. And another route with just the boat, the points and the boat IDs. Okay, let's color them again in bluish, so it will be clean and organized. Okay, that's it for now. In the next lesson we will take care of the gate that needs to open when the boat reaches the beach. So last but not least, we need to make this gate here in the front of our boats to open when they reach the beach. I mean, we already prepared it, but we need to copy stamp rotation. There's already a group which is called gate in your boat geometry, which is just the front part here. And now we put down a transform node, but just with gate. The pivot set it to $GCX, GCY, and GCZ. So it will put the pivot in the center of the group. And let's just display this one boat here. Okay, as you can see, the pivot now is in the center of our gate here, but we will need to move it down here. So with insert, you can move the pivot, move it. It's all, sorry, it's connected. So we need to for sure break the connection first. Now we can move it. Sorry about this. Okay. Very nice. So like here, it's nice, I guess. And now we need to copy stamp the rotation value. So we put a stamp expression, but first we need to enable the copy stamping here. Stamp inputs. You can also pack the geometry, will be more lightweight, and put it here. Let's call it rotate the variable. And okay, let's refer here to $open. It's not available at the moment because it's no local variable. So let's drop down attribute create and don't write any values. Just put here open again and the local variable also open. Okay. So now it's available. And so every value which comes in here for the points with $open will be written into the rotate value here. Okay, now we need to put it as a stamp here. And so it's copy one. So refer to copy one, and it's a rotate that we need, and default will be 0. Okay, now it should work. And as you see, it just opened the gate. Let's see if our copies also do this. Oops, sorry. Let's see. Yeah, all copies have opened their gates. So let's scroll back and see if they just open it when they arrive. Yeah, as you can see here, when they open their gate when they arrive at the beach. Very nice. Okay, so last but not least, we need our defenders. So just step one level up, create a new geometry, and call it defenders. This one will be really easy because we just need to load one file, which will be the defenders. So they also have some geometry up here. Yeah, that's it so far. We created the scene. And so in the next lesson, we can start with the crowd itself. See you there. Welcome to the next lesson. Now we will take a look how we can set up our soldiers. So let's create a new geometry node here, which we call crowd source. Okay. Here we will create an agent node. With this node, it's possible to load the agent we created in the earlier lessons. So we know that agent name here is soldier1, and the clip which we want to load initially will be the idle clip. Okay. So it says missing or bad objects. That's why we have to say that we want to load it from the disk because we already cached this agent out. Okay, now we reload it and there is our agent with the idle animation. If you don't see an agent, you can check up here the project folder. It should be set to the referenced file, so to this project files folder. If it's set here, it should load our agent properly. And it's also good to start with 07 underscore start because later on we will load some presets which might not be available if you start with a fresh scene. Okay, perfect. So now we have our first agent here. And we have to drop down a few more nodes to make this agent work also in the ragdoll system. This is all new in comparison to Houdini 14. So the two nodes we need are agent collision layer and agent configure joints. First, let's drop down the collision layer node. With this node, we can define the collision for every bone object in our soldier here. Okay, so let's begin. Here we create a new shape and then we have to select the bone we want to assign the collision shape to. So let's start with soldier head. As you can see, the presets that get chosen here are not so good in this case. So we can scale the bone until it fits. We also have to translate it here. So this is quite a bit work to get all bones properly for our soldier. So let's make it easier and just on this little wheel here up here, you can select the soldier 1 preset. For the mocap bipeds that are coming with Houdini are already presets created. In this file is also available the soldier 01 preset. As you can see, I set up all the bones with collision shapes to make it a bit faster in this lesson. But if you have your own character, you have to go through this process, select the transform here, select the bone, and create the proper collision object. Okay, next node is the agent configure joints node. This one is also necessary for our agent to work good with the ragdoll system later. With this node here, we can define the joint limits of every bone. So if the ragdoll gets activated, the joints don't do crazy rotations. If we doesn't use this node, it will be look a bit strange. Same process here. You have to select the transform, and then it automatically picks the parent transform, and it also has a really good visualization here. So you see the angle in which the bone can rotate later on. You can set some values here, and for example, limit left and right, the rotation to left and right more than the up rotation or something like this. Same here, we will pick a preset. On the wheel here, you see soldier 01. In this preset, I already set up all the rotations like they make sense. For example, that the knees here can just rotate up and down and not so much to the sides. Okay, so now we have our agent ready to get into the crowd simulation. To do this, we first need a source. So let's create the node crowd source. Okay. But before we get our agent into the simulation, you can also test if the settings you set here are right. So you can use this shelf tools up here. Just use this configure joins and select your agent. Hit enter, and now it set up a test ragdoll sim automatically here. We can delete this newly created configure joins because we have the one we created before. But now, if you select the test ragdoll, you can see still does some crazy rotations, but we will take care of this later on. But in general, it works. Okay, again, we can see, yeah. Okay, doesn't look too bad here. So our ragdoll is working. Okay, so this here is the crowd source where we can set up the initial layout of our agents. Let's see. Here we need the agents and here a custom object with points. So for example, a grid. As you can see, it automatically creates some proxy agents here, and you don't have to use a grid or something. You can also just define an area here to scatter your agents. But we have our boats, so let's object merge the boats in here into this object, and in the scene we have no, sorry, not the scene, the boats, we have out boats. Okay, as you can see, there are the planes, the grids with the boats. And now let's drop down a time shift because we just want the initial position of our boats. Okay, frame 1, break the connection here, frame 1, and plug it in here. Okay, as you can see now, our agents or the proxy agents are on the boats. But for sure, we want to use our soldiers. So put in the first input here our soldier. And as you can see, the soldiers are on the boats. Okay, let's make the other stuff visible. Up here, you can select ghost other objects or hide. In this case, we want to see the objects outside this geometry SOP. So let's select ghost other objects. And as you can see, our soldiers are on the boats in their idle simulation. Okay, very nice. Next step would be to define how many agents we want to have on the boats. So up here we will use the area size for scatter density. A few too many agents here, so let's bring down this value to 0.58. Okay, that looks better. There's automatically relax here. If you don't use this, they will start clipping into each other, which isn't so good. So you can crank up this value so the points get relaxed. And for the crowd system, we have to set the default state, which will be the idle animation as we already set up. And here the group name will be soldiers if you need to separate them from other crowd agents later on. Okay, you have some more settings down here, which will be interesting later on, like the minimal speed, maximal speed, turn rate, and so on. The initial velocity will be 0 because we will move them with the boats in the beginning, and the heading is also okay like this because we want them all to look to the front. Okay, but here are some more interesting options on the randomize tab. Because in many cases you don't just have one agent, you have several agents. For example, in this case, it could be not just a soldier with a rifle. It could be a soldier with a pistol, or it could be a medic, or someone with a rocket launcher, or something like this. So you can randomize the agent primitive. Now it doesn't have an effect because it's looking how many primitives come in here, and then it just chooses randomly between these 2 or 3 or 4 or whatever, how many primitives you have. Now we have only one, so there's no difference. But to set this up properly, so you know how to set up it with several agents, we will just copy this 3 nodes here, drop them down here, and let's call this one here soldier 1 and this soldier 2. Okay. On this agent node, we will pick soldier 2. If you copied the reference file folder properly, it should work because there I already created in soldier 2. Okay, let's see. We have to hit the reload button. And now we have to merge these 2 agents together here. Merge agents. Okay. And as you already see, there is a second agent here with another gun. Now this changed to 1 because the range is now between 0 and 1. Here you can adjust the seed if you want to have a different distribution. So seed 1 is fine for now. And also it would be possible to use a ramp to define how many agents from which type you want, but for now it's fine. Here are more options like that you can randomize the default state, their scale, which we can use now. So default scale will be 1. I mean, this difference is a bit too much. Let's say 0.5 here, and again a seed value. Then we can randomize the speed, the max speed, the initial velocity. But for now, just leave it like this. And now there's one more important thing to take care of, which is the constraint network we need later on for the ragdolls. So let's drop down an agent constraint network, which goes here. And here you have some settings for the constraints. For now, we just leave them like they are. Later on, when we set up the ragdoll simulation, we will go into detail with these values here. And now you have 2 outputs here. One is for the constraints and the other one is for the agents. So let's create 2 null objects, again with capital letters so we can pick them easily. Out agents here, and this one goes here, out constraints. Okay, very nice. So now we have soldiers on our boats and we can continue to the next step to create the DOPNet for the crowd simulation. See you in the next lesson. Welcome to the next lesson. Now, as we have set up the crowdsource, we are going to start with the simulation. I think the best way is to use this shelf tool up here in crowds and the simulate shelf tool, because then it automatically sets up the whole simulation network with the nodes that we need. Otherwise, there will be many nodes that we have to create manually. Okay, but to make this work, we have to take care of a few naming things inside here, the crowdsource. Make sure that this node is only called out. And here, constraints has to be written like this. Okay. Now it should work. We just select the crowdsource and hit the simulate button. Okay, here it is. Here's the crowd simulation set up, and also in the crowdsource, there's automatically created the stop import here, where the simulated agents get fetched again into SOP. So let's see here in the crowd sim. Okay, let's organize the nodes a bit. So down here is the output. This one here is new in 15. These are the ragdoll constraints. Also this part here with the bullet solver. Before it was just the transitions and the states and the solver itself here. Let's organize it a bit. Gravity. Here in the static solver, we can merge more objects to collide with our crowd. Here is the bullet solver. Okay, and so let's take a look. Here we have the transitions. So the transitions consist of two parts. There are the triggers and then the transition itself. So every transition needs one or more triggers. Very important here, the trigger name has to be unique. So if you copy these nodes, this node here, and there's the same trigger name inside, it will be a problem. So make sure this one here is always unique. For triggers, you have several types. You can take a look at the particle speed, use custom vex expressions, or just like it's here when the current state is longer than 0.4 seconds. That's a standard setup here. And then down here you have the transition. So you have to put in an input state. Now you can also use several input states. Like this, you don't need for every input state an own transition node. So the output state is this state in which the agent will translate if the trigger activates. Then you can set a duration here. So in this duration, the animation will be blended in the crowd solver. So every bone will look up the position from one state to the next and make a smooth transition. Also very useful here is the random time offset. So if you just have a crowd running and you want to have a few agents that slow down and go into a walk state, for example, you can use a random time offset so not every agent start at the same time with the transition. Okay, so we will customize this part later on. Then we will take a look here at the states. These are also very important. The states refer to the animation clips we baked out earlier. So make sure that every state has the exact name like your cached out animation. So for example, we cached out the idle animation. So let's change this one here from stand to idle. Okay. Normally here it's $OS, so it will use the operator name. So state name is idle, clip name is also idle. You can use different states and the clip names. So, for example, if you have several idle animations, you can use different names here. You can also randomize the clips, but for now, we just want to use our idle. Also new in 15 is the ragdoll option up here. So you can say that the ragdoll state, so when the agents goes into the state, the ragdoll system will be active. This one here is a standard ragdoll stage, which we will use later on. Okay, so another interesting thing are these nodes here in the stream of every state. So you can use custom wrangles or the pop steer forces to apply them to just one or several states. You could also merge several states here. But for example, this pop steer wander will only be active if the agent is in this walk state here. You can also use these nodes and put them down here. Then this state or this custom node will be active for all states that will be merged in here. That's important to keep in mind. Later on, we will use a custom wrangle here to make sure that our idle soldiers will move with the boats, because at the moment they would just stay in place here and the idle animation would be played, but they are not moving with the boats. We will take care of this later. So next, let's take a look at the solver itself here. You have some different attributes here on the solver. most important at the moment, and the animation behavior, let's put here the allowed variance only to, let's say, 5%. I mean, it's a good thing that the animations automatically get retimed to the speed of the particle. But the problem is if you have a run animation and you allow too much variance here, if it's really slowed down or speed up, then it just looks weird. So I think it's better to switch in another state if we want our agent to slow down or speed up. So let's keep the variance really low here. The subsets are just fine for the moment, timescale also. So let's take a look at the particle behavior. The standard setup that update particles is active here. Then the crowd solver will use the pop solver, which is in here for the particle movement. It's also possible to don't use this option and put a custom pop solver here at this place. But for now, just let this active, and we will take a look at the other values here. Drag is also fine. For some states, it's necessary to bring this drag down, the air resist, but then we can do this down here. Okay. Another interesting thing is here the look at. If you want that your agents look at a certain point, we will use this later on. The terrain projection we can set up right now. So if our agents move here over the sand, they will automatically be on the right position. So if there's a little hill, they will move upwards and be projected onto this hill and not clipping into it. For this, we have to select the subpath here and look for our scene and the out beach, because we want them to be projected onto the beach as soon as they step out of the boat. Let's select out beach here, and direction -1 in Y is fine. Okay. The agent feet adaptation is another feature that makes sure that your agent foot is not penetrating with the ground geometry, so it will modify the bone's position to keep the foot always above the ground. Then we have the avoidance. This is normally active, so this feature makes sure that the agents are not colliding with each other when they are running, for example, and they look forward into time in the sim, and so they anticipate the position of their neighbors, and with this feature, they make sure they're not colliding. We will modify these values later on, but for now, it's just fine. So this was a rough overview over the crowd sim that is automatically set up if you use the shelf tool. And in the next lessons, we will make many modifications to the system, add more transitions here, add more states, and use some custom nodes to make sure that our agents move with the boats, and set up proper collision behavior with the sandbags and the tank traps over here, and even trigger some ragdoll animation when they run into an explosion, which we will also set up later. So, see you in the next lessons. Welcome back. Now we will take a look how we can make sure that our agents are moved with the boats properly in the beginning. If we hit play now in our scene, we see that it's really slow, and that's not because of the crowd simulation, that's because of the copying of this boat objects here. To fix this issue, just let's move into the boats, and on the copy node here, just activate the packed geometry before copying. So now every boat is a packed primitive, and copying is really fast, as you can see. But still we see that our agents are not moving with the boats. To fix this, let's jump into the crowd simulation. Up here we have the idle state, which we just created in an earlier lesson, and it's based on the stand state, which was here before. That's why here's a pop wrangle, which makes sure that velocity and force is 0. That's not useful for this state, because in the idle state, we want our agents to move with the boats. To make sure that every agent gets the proper speed of his boat, we have to fetch the speed or grab the speed from the points of these boats which we created here. In the boats, we have the outboats IDs. These are just the points of every boat, and onto these points is the V boat. This is the speed of the boat. So we will fetch with a point expression the speed of every boat and assign it to the soldier which is on this boat. Okay, let's do this. Inside here, we will just use this wrangle here to assign the proper velocity to our agents. So v is fine, but we will use a point expression to grab the speed from our boat points. Okay, because this expression here is all in vex, we need an absolute path pointing to the node. So we will use the op expression and object for the object level. Then the sop is called boats, and inside there is the out boats IDs. Okay, the attribute we want is vBoat. Last but not least, we need an attribute on the agents to look up to which boat they belong. So as you might know, often you use just the point number, but in this case this won't work because we have several agents on one boat. But we created an attribute earlier which is called boat ID, which should be on every agent. So let's put in here at boat ID. Okay, that's just a warning which we can ignore. And just before we hit play, let's check if the boat ID is present on our agents. To do this, let's take a look in the geometry spreadsheet here, the crowd object and geometry. There you will see all the attributes which are on our agents. I already put some attributes up here, but we want also see our boat ID. And as you can see, it's 0. That's not like it's supposed to be. So let's jump back to the crowd source here. There is coming in our boat geometry, and there's no boat ID attribute present. So one step back to our boats, and here you can see it is present on the wrangle, but in this step it gets lost. That's why we need to use template point attributes here. That makes sure that all the attributes which are here on the points get copied to the geometry. Okay, now boat ID is there. Perfect. Let's jump back into the crowd simulation and again hit play and still not moving. So another important thing we need to take a look is on the state here, the in-place gate speed. The in-place gate speed is a really important attribute because if you read the description, you might think that it only tells the crowd system how fast the animation of the state is allowed to be played back, but that's not the case. It also limits or influences the maximum and minimum speed of your agent in the state. So that's why our agents here are not moving, because the in-place gate speed is 0, because this was before the stand state. So let's point a number, for example, 4.5 here, and take a look at geometry spreadsheet. As you can see, both IDs are fine now. And let's see. So if we hit play, now our agents start moving. Very nice. But we want to see our boats as well. So just set your display flag here, back to the system, and let's see. Okay, they are moving with the boats, but it looks like they are a bit slower than our boats. And this we need to investigate a bit more. As we scrub through the simulation here, we can see that the velocity value in the z direction is 4.275. Let's take a look on our boat geometry, how it's supposed to be. If you take a look here, v boat in z direction is 4.32. So our soldiers are not moving with full speed. There are several reasons for this. First, let's take a look at the crowd solver itself. there is this drag value here. So because our agents are particles in the end, they get dragged, and I think it's better to set it individually for every state, the drag value, and not globally. So just let's put a 0 here, and the drag in the system is called air resist. So let's put the air resist to 0 for this state. Okay. But let's take a look. The soldiers are still not moving with full speed. And to explain this, we need to take a closer look to this in-place gate speed. As I've said before, this not just influencing how fast the animation gets played in the state, it also has a big influence on the speed max and minimum. But as you might remember, on the crowd source, there's also an option for that. Here on setup, there is also the minimal and maximum speed. But you just saw in the crowd system that it's 4 point something, so we need to see what's going on. Let's first set the maximum value here to really high number, because in the crowd system it's more controlled by this in-place gate speed, so just don't limit it here. Let's set it inside the DOPNet, and now you can see that it changed. Before it was here the same value because it was limited by this value on the crowd source. Now we have a better control because this value here is the important one, and then it takes into account what you put in here, the variance. So 5% more than this in-place gate speed and 5% less than this in-place gate speed. Let's set this to 10%. And take a look again in the geometry spreadsheet. Now we have some variance here about with 10% more and less. And if we play back now, we can see that our soldiers are moving with the proper speed, because the crowd solver takes into account which is speed max and speed minimum. Here you can also see how the clips gets retimed into this 10% range. One would be the normal speed, and here's for this, for example, this 0.95. Yeah, I hope this wasn't too confusing now, but just let's recap that it's really important how to set this in-place gate speed, and to keep in mind that it influences the minimum and maximum speed. For this state, it was even more confusing because we wanted to set the velocity to a specific value. But for the other states later on, we will just modify the in-place gate speed to a value how it fits to the animation, so they soldiers don't run too fast or too slow. Okay, we reached our goal for this lesson. The soldiers are moving with the boats, and in the next lesson we will set up some triggers here to switch the soldiers to another state when they reach the beach. See you there. Welcome. Now we will take a look how we can add additional states to our crowd and do some transitions between them. So as you can see, I added some more nodes here to the scene, an environment light, a sunlight, just to have a nicer representation here in the viewport. You can also just start from the scene file here, or continue from the previous one. So let's see. I already simulated to frame 350 here, and as we can see, our soldiers just stay into the boats. They are not start running on the beach. So now we will fix this. Let's dive into the crowd simulations. And in the last lesson, we cared more here about the states. And now we will take a look at the triggers and transition. So a trigger is basically an event in the crowd system that triggers a transition to another state. So in this case, we want to go or do a transition from the idle state we set up in the last lesson to the next state, which is in our case not the walk state, it is the run state. So let's call this one here run, and it will automatically load the right clip now because it's also called run. And as you remember, the in-place gate speed here, we have to set to a proper value to define how fast our particles are allowed to move in this state. So let's point 4.5 here. And let's jump back to the beginning of the crowd simulation. Okay, now the run state here is set up fine. The pop steer wonder we will take a look later. So now the trigger. We want to set up a custom trigger. Um, Very important for the triggers is that they always have a unique trigger name. So let's call this one here crowd trigger landed and put here just $OS to use the operator name. If you have two triggers with the same name, it won't work. So keep this in mind. Next thing is the type here. So Houdini provides several options here. So you can just trigger because of the particle speed, RBD impact data. For example, if the agents get hit by an object, you can just switch them to the ragdoll state, or how long they are in the current state, which we will also use later on. But for now, we will use a custom Vex expression because we want to have them switch into this transition when a specific attribute, which we already created here on the boats, is an attribute here, as you can see, landed. And in the geometry spreadsheet, you see at the beginning it's 0, and when the boats reach the beach, it switches to 1. And if the attribute is 1, we want our agents to start running. Okay, let's do this. In the crowd simulation, we need to use again a point expression here to set the trigger to 1. If we set it to 1 here in Vex, it will enable the trigger and the transition here will happen. So here is important, you have an input and an output state. In input state, you can put several ones, also new in Houdini 15. Important here, even if the trigger is successful, but your agent is currently not in the stand state, it won't do the transition. So with this, you can just trigger agents in a specific state, for example. We just want to trigger our agents in the idle state so that they switch from the idle to the run state. Okay, the duration is the time in seconds, how long the transition and the blending of the bones will happen. 0.25 is fine for the moment, and the random time offset will make it look a bit more random and not so similar, so that every agent start at the same time with the transition. Okay, so the transition is nice here. Let's just call it idle run. Okay, but now we need to set up the trigger properly. So we will use again a point expression like we did here in the wrangle, where we transferred the velocity to our agents of the boats. Let's name it properly. Follow boats. Okay. So let's just copy this point expression here and put it here in an if expression. So if the point expression, but in this case we don't need the velocity, we need the landed attribute is bigger than 0, we want to set the trigger to 1. So like this, we again do a lookup individually for every agent on every boat. So that's important because not all the boats reach the beach at the same moment. So we need it per boat. Okay, but we have our boat ID here as the attribute, as the lookup attribute, so it will work fine. Okay, let's see. This warning here we can ignore, and let's switch it here to 350 or 60. Just let it simulate until there, and then we will see if our agents start running. You could also have done this trigger with the proximity to the beach. So when the agents gets near to the beach, they start running. But in this case, I think it's nicer to do it with this attribute because later on you will often need specific attributes to trigger something. So I thought it would be good to put it in here, how this works. Okay, as you can see, very nice, our agents start running. Just let's simulate a few frames more here to see if the speed of our agents is fine here. Okay, I always recommend to do a short flipbook here. Just click here and then flipbook with new settings. We want to do it from, let's say, 300 to 400 and hit accept. Now a new window should open, as you can see here, and now it will cache it here into our memory and we can see it in real time. Very useful. Yeah, I think the speed is nice of our agents, but as you see here, they start to switch a bit late into the run state. So they start moving but are not running. So the animation is not playing back. That's not because of the duration of the transition here, that's because of the random time offset. Because with the random time offset, it will do 3 seconds before or later the transition. And in this case, because we want to have them start running when the gate opens of our boat, we will just put point 2 here and just resimulate it until this frame here really fast. Another thing we need to do is to keep in mind that we have to put the air resist back to 1 for the run state, because we just put it to 0 in general and said that we want to set it individually per state, and the run state will need a drag from 1 because the agents are moving the particles. Okay, so as you can see now, it's much better. The agents reach the beach and immediately start running. We have some intersections here, but we can take care of this later. Okay, so about the air resist. Because I don't want to resimulate this right now, just down here you can hit the button of this little brains here, and then even if we change something, it won't automatically resimulate. That's very useful if you first want to do some changes and not resimulate for every small change you do. So here we set the air resist to 0 with this wrangle. So let's just copy it here. Bob wrangle air resist, and this we don't need. Just put the air resist back to 1 for this state here. Okay, so now the last thing we will do in this lesson is to take a closer look at the Pop Steer Wonder. This is the first crowd steer force we will use. Later on, we will use some more. Here you can see it's used as a crowd steer force. You could also just use it as a normal pop force. For example, if you have some normal particles not in a crowd system and you also want to use the features here, you can just select it as a normal pop force. But for us, crowd steer force is right, because then we have a weight parameter here. And so if you have more than one crowd steer force, the weight is very important to set which steer force should influence our agents more. So the Pop Steer Wonder is just for getting our agents to move. We just have a force of 10 here in the Z direction. That's why our agents start moving in this direction, which is fine for us. Down here you have a noise tab. You can set the amplitude, the swirl size, as you know it from the normal noise features you use with particles. And here are some custom wax expressions to make it look a bit more natural. For us, the noise is fine here at the moment. It just makes it look a bit more natural that our agents not all are moving directly in this direction. They start to swarm out a bit here and here. So yeah, very nice. We have set up our first trigger and transition. More will follow. Welcome to the next lesson. Let's just add one more trigger, transition, and state here. Because now our agents are all running, but as you remember, we have also the run shooting state. So before we're gonna take care of these obstacles here in the next lesson, we will set up this transition as well. So just create a new trigger, and now we going to call it crowd trigger run shoot. And now we want to use the current state duration so that they switch. For example, after running for 2 seconds or 1 second, they gonna switch to this run shooting state. So comparison bigger than, let's say, 1.5, and do a crowd transition now from the run state to the run shooting state. Okay, now we're gonna use this random time offset so not all agents start at the same time shooting. We just put here random time offset 1.5. That's nice, and the duration can be really fast, so 0.3 is fine here. Okay, let's call it crowd transition run shooting. Okay, just merge it into the merge transitions here. And for sure, now we need to set up this new state. So for this new state, we also want to reuse the pop steer wonder and the air resist. So we don't have to copy them again. We just copy our run state here, call it run shooting, drop down a merge, and like this it will work fine. So we can reuse this pop steer wonder and the air resist node. Yeah, let's step back in this case. Don't forget to reactivate the simulation down here. Now the bar is gray again because it needs to resimulate everything. And let's see if our agents start switching to the state. Later on, we will also set up the reverse action so that they switch back from the run shooting to the run state, but this we can do later on. Let's first check if this works properly. And so now it's simulated. Let's zoom in a bit and see. Yeah, they start shooting here. This is a shooting animation. We can do again a flipbook to see it a bit better. Just do a flipbook here again. 3 to 400 is fine. Hit accept. And let's see. Here's our flipbook. And it's just overwriting the old one. Yes, that works very nice. So our first and our second transition is working well. Yeah, that was it for this lesson. In the next lesson, we will take care of the obstacles so that our agents don't run into the tank traps and the sandbags. See you there. Welcome to the next lesson. Now we're gonna take a look how we can set up these tank traps here as obstacles, and how we can improve the performance of our crowd simulation in general. And for testing purpose, we will isolate just one boat so we can simulate faster to check if the obstacles work properly. Okay, here in the crowdsource, we have all our boats incoming, so we get the whole army. But now we just want to isolate one boat, let's say this one here. And to do this, we just going to use a blast node to have it more procedurally. And here we're gonna want to say points and use the attribute at boat ID equals when boat ID is 4. Okay, let's see. Now this one was deleted, so we want to delete none selected, and now we stay with this grid here, which is perfect for our test. And also the idea is to have our crowd simulation start later when the soldiers already arrived, so we don't have to wait when we test the obstacles always the first 300 frames until they arrive at the beach. So let's put here with our time shift, there's at the moment frame 1, let's say frame 300. So the boats are already here at the beach. Okay, let's color these nodes red so we know we have to deactivate or switch them back later on. But for now it's fine. Our soldiers will start here. And also set it here in the crowd simulation, the start frame to 300. Okay, very nice. So let's see if we get now our crowd here on frame 300. Yeah, here are our soldiers. Okay, next thing is to check the performance of our scene. To do this, we're gonna use the performance monitor. I always recommend doing this from time to time because sometimes there's one node slowing down everything which is not necessary. For example, an attribute transfer or something like this. Okay, so let's just record the performance, reset the simulation, and let's step, for example, to 480 and let it simulate until there, and we will see which node consumes the performance. Okay, so you can see the boats here, the solver, and also this attribute transfer here is consuming quite a lot of time. And in the crowd sim is the solver and especially the agent terrain projection. Okay, so let's check if we can do something. Okay, here in the boats, as you can see now, the nodes are colored. It's attribute transfer, which transfers the attribute open and the rotation of our gate from the beach to our boats. And it looks like, because it's taking the whole beach geometry here to copy or to transfer to our boats, it takes a lot of time. And that's not absolutely not necessary. We just need a small stripe of our beach here. So let's use a blast to shrink our beach until here. Okay, so let's use a blast here. And let's use the position at P and the Z direction, because this direction here is Z in our scene. And let's say if it's less than, let's test 20 minus 20, it will be deleted. So let's see, hide other objects. And now if we have to primitives, sorry, points. Yeah, now you can see we can shrink our beach here based on the Z position. So let's put it like this and drop down an poly reduce, which is also really useful. And it will reduce, let's say, stiffen borders, stiffen features, equalize edges, and bring it down to, let's say, 10%. Okay. Now 556 points before 40,000. That looks good. And now this attribute transfer here should work faster. Okay, the other thing was the terrain projection. There, I think there's also the issue that our beach geometry is really high res. So here we will also use the polar reduce, but just for our beach, which we'll use for the terrain projection. For the rendering, we will have our nice looking beach here. So let's duplicate this node here. Let's call it out beach projection. Okay. And drop down another poly reduce here. I mean, we have to make sure that we don't reduce it too much, that otherwise our soldiers will float in the air if there's only one big primitive here for a large space. So again, this here, and let's look through this, let's say 20%, for example. Or, I mean, we can even go down lower, 10%. Yeah, the big features are there. Really good. And now we have to reference to this node here in the crowd solver. Don't forget to set it back here so we see it nicely. Okay. And in the sim, we have to reference here in the crowd solver at save at the terrain, we have to reference to our out beach projection. Okay, now this one should also be much faster. In general, it took before about 20 seconds until frame here 480. We're gonna check this again now with all these optimizations here. Okay, record again and 480, and let's see if our optimizations did something. Yeah, that's quite faster. Now the crowd solver itself only 4 seconds, and the attribute transfer is really fast now. So it's always a good idea to take a look at the performance monitor. Sometimes there are some issues with some nodes which are really easy to fix. Okay, so let's shift the obstacles to the next lesson. See you there. Okay, welcome back. Now we will take a look at the obstacles. Dive into the crowd sim, and for the obstacles there's already a node in Houdini in the crowd system which is called pop steer obstacle. We will drop it here between the merge states and the crowd solver because we want to apply it to all of our states. If you just want to apply it to one, you could also drop it here in the stream from one state, but we want to have it active in all states. So let's take a look here. We at the source we can use different inputs, but we gonna use a sub input, and the sub path will be out tank traps for now. Okay. Then we have several values here. The most important ones are these force values here, because we already have some other forces here in our scene, and the Wonder Force, for example, and we need to make sure that this obstacle force is higher than the other one, so our agents will avoid the tank traps. Also, it's important here to switch output attribute to crowd steer force, because you could also use it with a normal particle system, but in this case we have the crowd, so crowd steer force. The weight here is also important uh, because here you can see on the Wonder the weight is 0.5. So in the crowd solver, this obstacle force will be more important than this pop steer Wonder, which is fine. Okay, let's take a look at our tank traps here. The geometry is really thin, and I think it's better to use some proxy geo here to make it also faster for the race, for the collision detection. So just copy this copy node and drop down a bound. This one here will automatically generate a bounding box for your tank trap, which looks like this. Tank trap, bounding box. And now we will copy this bounding box into our scene, as you can see here. Okay. Well, let's see. Template this one here. Okay. Yeah. Just let's enlarge this bounding box a bit to view, so we have a better collision. Okay, that looks good. And copy this node here. Just call it out tank traps collision. Okay, don't forget to set it back to here, the display flag. And now we have to switch it to our out tank tracks collision here. Okay, that looks good. And now it's time to do a small test run here. Okay, let's say until frame 600, for example. And I always recommend to just click here, then it will simulate really fast because it don't have to display the viewport, and you can see the result immediately. Okay, let's see. If we step through, we see that our soldiers are avoiding the obstacles, but they react really late. The soldier is already colliding and it's a bit too late, the avoidance. So let's take a look at the attributes here. As I already mentioned, these forces are really important and also the surge distance to the side and to the front. I mean, to the side is not so important at the moment, but we want to have that our soldiers know earlier that there is this obstacle. So let's put for the front surge distance 40 meters. Um, and another important thing is the field of view, horizontal and vertical. Let's update this horizontal view to 160 degree, and samples just mean how many rays are shoot out from the soldier's point of view to into the world to see if there's an obstacle. So the collision avoidance will be more accurate, but for this one, 64 is totally fine, I guess. If you have a higher value, for example, if you have a really fine collision geometry, keep in mind if you put a higher number here, the computation, the crowd system is more intense and it takes more time. So it's always good to have some proxy geometry to represent your objects, I think, like we did for the tank traps. Okay, so 40 is nice. Side search distance is not so important here, because if they're already here, running here, it's not, they don't need to know that the tank traps are at their side. Um, and for the forces, I think we should also put a higher value like 15 and 10. Okay. Again, let's simulate until 500 and we will see if our changes that we made here make sense. Okay, let's take a look. Soldiers are coming and yeah, much better. Now they anticipate the obstacle earlier and so they can run in a nice and a smooth curve like this around the obstacle. It looks much more natural. I mean, this is a not moving and big obstacle, so they could even see it from, let's say, 150 meters. But I think it's not good like this. As you can see, nice avoidance here. If you progress, they also avoid the second one here. Okay, so I think now you also understand why it was important to set up the crowd simulation to start at 300, because we had to do several tests here, and if you always would have to wait until it simulates until 300, it would be really annoying. So in general, I always recommend do a test scene or a light version of your actual scene just to test out new features. Okay, yeah, very nice. If you want, you can also test it with the whole army. It will take a bit longer, but it's also just fine. And I mean, the optimizations we did are also good for the whole army, so it will simulate faster. So that's it for this lesson. In the next lesson, we're gonna take a look how we can use these tank traps here as an object where our crowd tries to hide behind it. Our soldiers will stop behind the sandbags here. Some will start running again. Others will go into another state. So all this we will take a look in the next lesson. See you there. Welcome to the next lesson. Now we will take a look how we can introduce a new behavior for our agents so that they can hide behind the sandbags. So first let's switch to another test group, because these agents here will just run in this direction, but we want some that run directly to the sandbags. So let's see in the crowd source. Let's switch to another ID here. 6, yeah. 6 is good. They will directly run into the sandbags here. At the moment, they will just run through the sandbags because they aren't set up as a collision. As you can see here, yeah, they just run straight through. Okay, so let's set up this collision at first. like with the other objects, we want to create us some proxy objects for the collision, like we did with the tank traps. So just copy this here and put it here to the sand barriers. Same method here, like this. Okay. Now let's call this out sandbags. Okay. Let's get a bit of space here. Yeah. Okay. Let's see. That is the bounding box for the collision. Let's make it a little bit bigger so there's no gap between the two. And a bit smaller in this direction because later on the agent should stand here behind the sandbags and it will be a problem if the system detects a collision there. But like this, it's good. Okay, so the sandbag collision is set up. Now we need to do it in the crowd system. We already used this pop steer obstacle here for the tank traps. And now let's introduce a new one, which we call sandbags. And here we just have to pick the new created sandbag collision. I think we're gonna modify these values a bit because in this case it's fine if they get near the sandbags, but for sure we don't want to that they collide with them. So let's increase this near collision force here to 25. Also the front search distance, and I noticed in a few tests that perhaps we need a few more samples here, otherwise they will detect the collision too late. So let's increase the samples to 256. Are just the ray samples that every agent shoots out into the direction you can set up here to detect the collision. Okay, so let's give it another try. And let's see our scene here. Back to the merge. Okay, and let's step to a later frame to see if our newly set up collision with the sandbags is working. Okay, yeah, that doesn't look too bad. They split up here and just run around our obstacle. Very nice. Okay, that was the first part. Now our agents avoid the sandbags, but as I said, we want to have them hide behind the sandbags or just stand there and get to the ground. So next thing we want to use is the node which is called popsteer_seek. It's a seek behavior, and you can define a point or several points in the space, and the agents which are assigned to this popsteer_seek will try to get to these points. For sure, everything weighted with the weight you can set up here because it's a crowd steer force. So internally, the solver will look up how you set the weight for every behavior and try to balance it. Okay, let's create this popsteer_seek and drop it in this stream because we are still in the run and run shooting state. Okay, let's call it popsteer_seek sandbags. As you can see here, one possibility is just to create a position. You can use particles, surface points. In this case, we want to use points which we will define in SOP level. To do this, let's jump back to our scene and create one more time a proxy object which will be used for the goal points. So here we have our sandbags that get copied, and we want to scatter some points on them just to create the goal points in front of the sandbags here. Okay. That's fine. Now we're going to use a transform. Move them back about this value here. Okay. And then we're gonna scale them to 0 because we just want to have them on the ground. I mean, it's not important if they're not 100% on the ground, but they shouldn't be up so high in the air. Okay, that's good. Now let's create a new out node here. Let's call it out sand barrier points PTS. Okay. Okay, back to the .NET and to our sim. Oh, let's just set the display frag properly. Back to our crowd sim, and now we can pick the newly created points here. Send barrier points, accept. Okay, we want to do an average position, and let's say we want to use 1000. It will just build clusters of the individual points, so every agent will be assigned to one cluster. And because we scattered behind all the sandbags here, we want to make sure that we have enough clusters for the agent to be assigned to. Okay, so now we're gonna take a look at the force here. The force just says how strong the agents will be forced into this direction. Also, we want to make sure that it's a crowd steer force, and the weight will be 0.6 because the collision here is more important than this pop steer seek. Okay, let's say 100 for the force as a start, and with this distance, every agent, even if they are really far away from a sandbag, would start looking for it, and that's not what we want. We just want that they will hide behind them if they are near the sandbags. Okay, so let's give it a try and see what's happening. Okay, yeah. That's the behavior I expected. The agents are just running crazy around this goal objects here because they are still in the run and run shooting behavior, but want to reach their goal points. So they are just running around all the time around the sandbags here. Okay, that's good. The next step now would be to introduce the new states down here and the transitions. So we have a new state behind this sandbags here, and it has to switch to the state if they are near the sandbags and if they are in a group, because we don't want to have all agents here to stop behind the sandbags. We gonna set up a new group to which randomly, let's say 10% of our agents gets assigned, and they are gonna try to hide behind the sandbags here. So let's start with the group. We're gonna insert it here. Here are the pop steer seek, and we gonna use the pop group to create our sandbag group. Pop group sandbags. Okay. We call it just sandbags. We want to have a random assignment of, let's say, 0.16 and pre-reserve this group. So at the beginning, the solver will add 16% of our agents have the chance to get into the group, and this will stay into this group. And here, now we're gonna assign this group. So only the sandbags agent group will get affected from our pop steer seek. Let's see if it works. Yeah, that looks very good. Just a few agents start with this strange behavior, running around the sandbags. The other ones are just going on with their way and trying to avoid the tank traps. Okay, so the next step now is to add these transitions I already talked about, but this we will do in the next lesson. See you there. Welcome to the next lesson. Now we will add this additional transitions. So we need a trigger and a transition, and here's a new point in this lesson. We also need a condition, so a logical element, because we need an AND. We wanna just have them stop if they are near the sandbags here and if they are in the sandbags group. Otherwise, we don't want to trigger the transition. So let's do this. Just copy this trigger here and use it here for the distance at first. So let's say object distance and point cloud. Here we're gonna again point to our sand barrier point object, which we created earlier, which is here. And the search distance is just 10 and the comparison distance is the important one. So we just wanna get this trigger activated when, let's say, they are less than 1.5 meters away of these points here. So they just will stop around here. Okay, let's call it crowd trigger idle, idle near sandbags. So this is the first one. And let's create this transition first to see if the first one is working. So create a new, or just copy this crowd transition here. And in this case, we want to switch from the run, which is fine because they are either in the run or in the run shooting. So we will just put here run and run shooting, and the output state will be idle shooting because at first we want to have them stand behind the sandbags shooting. So let's set up a bit shorter duration of the transition, and the time offset shouldn't be so long because otherwise they will run into the sandbags before they stopped. Okay, this is good. Just connect it here. And now we need to make sure that this idle shooting state is available. So let's just copy our idle here, call it idle shooting. Okay, let's do random time offset here, and we need to create a pop wrangle to make them stop. So let's just say that the velocity is 0 in this state, and also the force is 0. Okay, good. Let's connect it, and now our new idle shooting state is set up. The transition and the trigger is also set up, so let's see what's happening. So they're reaching the sandbags, and now, yeah, they stop like we expected. But these here also stop, and they shouldn't stop because they aren't in this special sandbags group. So now we need to set up this end condition to make sure that just the ones stop which are in the group. Okay, this is the first time that we use this logical element, which is just called crowd trigger logic. And the AND operation is fine. Here are several others you can use, but we need the AND for now. And copy this trigger, and let's call it crowd trigger idle near sandbags group check. Okay, so in this case we just gonna use our custom wax expression to check if our agents are in the group. The way we do this is also a new feature in Houdini 15. So let's take a look at the spreadsheet here, because we need a way to use an attribute to see if they're in a group or not. But this is easily possible with Wax. So let's see in the geometry attributes of our agent here. In Houdini 15 we see that all point groups also create a group attribute on our points. As you can see here, here is our group sandbags, and here are the 3 soldiers which are in the group. So as it's an attribute, we can just use it in Wax to see with an if condition if they are in the group. So let's say if at group, and here's the important bit, you cannot use the colon sign which you see here, you have to use the underscore to get the right attribute. So group sandbags, okay, is bigger than 0, then we want to set the trigger active. So e at trigger equals 1. Okay, very good. This should work. And now we're going to connect it to the end trigger logic here, and let's give it another try. Now only the agents which are near the sandbags and are in the sandbag group should stop. Let's see if that works. Another thing we need to take care of later on are the intersections here, because at some point the agents get to the same point and we want to make sure that they are still separated. Yeah, that works like expected. Only the agents which are in the sandbag group try to stop here. The little guy here is a bit confused. He's first running around the sandbags, but we will fix this later on. Okay, that works very nice. You can see they stop behind the sandbags and start shooting. Okay, like I said, at some point they get dragged to the same position here, so we're gonna introduce another new node, which was previously in the solver. Now it's a separate node, which is called pop steer separate. Here it is. Just drop it in here. And with this node, we can make sure that there are no intersections between our agents and they try to separate from each other when they are in a specific search radius. So again, we're gonna set it up as a crowd steer force. Let's point here. Let's put here 1 as a weight and 100 as a force. So we make sure that there are no intersections. So the braking force just says that it uses a little bit lower force if they're getting near to each other, but before they are colliding. This force will apply when they are nearly colliding. So here's our field of view, it's fine, and the search radius also. And we want to force the separation, so we definitely make sure that there are no intersections. Okay, good that we set it up now. I mean, there were no intersections, but you can imagine if we just activate all our soldiers, there would be definitely some intersections. Okay, now our agents stop and we set up that there are no intersections. So the last thing we're gonna do in this lesson is to set up a new state that some of our agents switch to crouch behavior. So to do this, let's set up a new trigger, and this is similar to this one. We just going to have a crouch idle crouch, and we again want to use the current state duration. That means if they are longer than 1.5 seconds in the state, they're gonna lay down on the ground. For sure we're gonna put a random value here as well. Okay, and we need a transition. Okay, so idle shooting to idle crouch we want to have here. And in this case, we want to have a greater time offset, let's say of 2, and as well a longer transition. Okay, just name it properly here. Crowd transition idle shooting to crouch. Okay, crowd trigger idle crouch is fine. Now we're gonna put it here. Here we also have to put the correct naming. Otherwise later on it will be really confusing. So run shooting to idle shooting. Okay. So to make this work, we also have to add this new state. We can copy this one here because the idle crouch state is also a static state where we need this wrangle here. Pop wrangle static. Okay. And let's copy it. Call this idle crouch. And let's see if that is working. Now a few of our soldiers here who hide behind the sandbags should switch to this new crouch state. Yeah, that's working. As you can see here, this one is stopping and then he's just switching to the crouch shooting state. Okay, just to make sure that our agents stop properly here, we're gonna increase this range here to 2 because otherwise some of our agents just pass by before they stop, and that's not what we want. Okay, now let's take a look again. Later on, we will also introduce that not all our agents enter the crouch state and that they can switch back to the shooting state or even start running again. Yeah, that looks better. Now the agents stop here a bit in front of our sandbags. We will tweak this behavior later on. But yeah, for now it's fine. Some agents pass by, some are hiding, and the ones who stop pass to the crouch state after a few seconds. So that's it. In the next lesson, we will take a look how we can add a live attribute to our agents so that randomly some will get hit while they are running and just fall to the ground. Okay, see you there. Welcome back to the next lesson. Now we will take a look how we can set up a live attribute for our agents and then use this die attribute when it reaches 0 to trigger the die animation. The idea here is to use a static point cloud and an attribute transfer to set this attribute. So instead of using our original agent points of every agent here, we will use this static point cloud so it's better controllable which agent dies. Okay, to do this, let's jump into the crowd source because here we have all our agent points, but I think it's a bit inefficient if we use the original position because they are spread out all around the scene. So instead, we will create our own point cloud, but link this one to our agents. Okay, so let's create a grid. It's fine to have it in the origin here. Let's take a look. Here's our grid. And let's scatter points onto this grid, and every point will represent one agent. Total count 1000 at the moment is way too high, so we will link this count to our agent number. To do this, just use the endpoints expression, endpoints, number of points, and in this case we need the out node here. Okay, out, that's fine. Okay, very nice. 9 points now, but because at the moment we have 9 agents. So this is all procedural. If you change the number of the agents, so perhaps, for example, deactivate the blast here, now we are back to all our 121 agents, then you already saw it switched to 121 points. So the advantage that it's all static here in the center is that we can easily animate a sphere or something to transfer this attribute, for example, the live attribute, and later on more attributes. Another thing is that all the points are random here from the point number, so the agents will randomly get this new attribute and not from the left to the right or something like that. Okay, now we have our scatter here, and now we need to set up these attributes we need. So to do this, create a point wrangle. And the first attribute we want is live. So we create an integer, name it live, and it's 100 at the beginning. Okay, next thing is the ID. So because we want to link our agents in the DOPNet later on, so we set the ID just to the point number. Okay, and last thing, we just create a color value of white so we can better see our attribute transfer. So 1. It's a vector, but you can also, if you want all 3 float values at 1, you can just use it like this. Okay, as you can see, all points are white now. So next step, the attribute transfer. Okay. And as a transfer object, we use a sphere here, do ISO offset to create a volume, then scatter in the volume. Okay, there we have our sphere. And now we need to create these attributes here as well, with other values so we can do a smooth transition. We don't need the ID, and CD will be 0, that it's black, so that we can see it clearly, and live is 0 as well. Okay, attribute transfer, and we just want to transfer the color and live. Okay, at the moment all points are black because the radius is standard at 10. So let's do 1 and blend 1. Okay. I mean, for now, we just going to switch if live is 0. But if you would like to do a more complex system, you could also say if live is below, let's say 50, then the soldier slows down and uses another animation where he's just running slow or crouching, something like that. But for now, it's fine that it's going to 0. And now for sure, we need a transform here just to animate our sphere, because at the beginning we just wanted to have it really small, and later on the agents will start getting this new live value here. Okay, for example like this. Let's deactivate the simulation for a second, and let's say starting from here we're going to start the animation until here. So now let's put here 15. Nearly all soldiers died, just for the testing at the moment. Okay, that looks good. And we will increase our total count so that there's no agent that switches back to another live value once it's already at 0. You could also use a sub solver here, but as it's all static, so for now it's fine like this. Yeah. Okay. Another advantage of the static point cloud. Very nice. Let's step back here and activate our blast again. So we just get our testing group, and you can see all that in the end. Okay. Don't forget to create an out node here. Out. Let's call it properties. Okay. Very nice. So now we set up our agents here. So the static points with the attributes. Let's take one more look at the geometry spreadsheet. If this is working, yeah, you can see the live attribute is at 100 in the beginning and gets down to 0. So the next step then would be to jump back into the .NET and create our new transition states and the trigger. So let's copy this trigger here and just call it crowd trigger die. So here again, we cannot use a current state duration or something. I mean, it would be possible, but we want to have it more controlled from our attribute transfer. So we select again this custom vex expression. And it's a bit like we did with the landed attribute here. We also referencing to an attribute on top level. So here again, we're gonna read this attribute from our property points. So let's do an if expression here and say if the live on the property point is 0, then we're gonna activate the trigger. Okay, point expression, and we need the op here. Sorry, op, and it's object. Oops, object crowd source out properties. Okay, we want to have the live attribute and add ID as a lookup. Okay, smaller than 1, or let's say 5 here. Then we set the trigger to 1. Okay, so that's our crowd trigger, and now we need to add the transitions. So we will need two transitions because the one possibility is that our soldiers are running or run shooting and dying, and the other one is that they're already standing here behind the sandbags and are dying. So, I mean, we can put here multiple input states, but only one output state, and we have separate animations. One is run, die, and the other one is idle, die. So, just copy this here, and it's from idle shooting to idle die. Okay, not such a big time offset. Okay, idle shooting to die, and the other one is from a run and run shooting to run die. Okay. Okay. So now all the transitions are also set up. And plug them into the merge transitions, what we have down here. And next is to set up the state. And here it will get a bit involved. We have to use Vex again because the problem is, let's just set up the state here, then you will see what the problem is. So just copy the idle, for example, call it run die. Okay, now it's set up. Let's step back that the crowd simulation gets resimulated. Don't forget to activate the simulation down here again. And let's give it a try. So our soldiers start like before, but now they should get triggered. Yeah, as you can see, here the die animation, this one for example, switches here, he gets hit and switches to the die simulation. So now we see multiple problems. The first one is that he slides over the ground once he's fallen down. And the second one is that the simulation starts again once it played once. So two things we need to fix. Like I said, we need some Wex code for this. As it takes some time, let's do this in the next lesson. See you there. Welcome back. So, like I said, now we will use some Wex code to avoid that our agents slide over the ground once they are dead, and the next thing is that the animation won't be looped over and over again. So to do this, let's drop down a pop wrangle here. Oops, sorry, pop wrangle. And to do this, we need to take a look at some attributes here. So open up the geometry spreadsheet and let's take a look at the crowd object geometry. Like always in Houdini, you have nearly access to all attributes. You can modify everything. You could even go into the crowd solver and modify all the pre-set up logical stuff. So you can see here are many attributes and you can modify nearly everything. So for us, really interesting are two attributes at the moment. One is the clip time and the other one is the state. So let's take a look at these two. You can put in here, up here, some attributes, even with wildcards, to just see them. The state attribute just tells you in which state the agent is at the moment. So we have our 9 agents here, 0 to 8. And here you can see some are in run shooting and some already switched to run die. And the next one we want to take a look at is the clip times. Clip times. Okay. So what does this mean? The first one is the clip time of the current state. So this agent here is just in the run shooting and he's already 1.35 units in this state. So it's a time unit. And the second one is if he's in a transition, then it plays both animations, both state animations. So first one is continuing to count and the second one already started. So this one is still the run shooting and the second one, which is coming there, is the run die. So as you can see here, he already switched over to the run die because the state attribute switches once the transition is finished. So he's still in the run shooting, 1.5 units, but the transition already started to the run die or whatever the next state is. There's also an attribute next state, but for now that's not interesting. So we will use these two attributes to get rid of our problems. The first one is we need to tell him if the state is at run die that the velocity should be 0. So the agent doesn't slide over the ground. But the problem is at the beginning of our run die animation he is still running. So we need to take into account at which clip time he is at the moment. And not the second one because this is transition. We need to take a look at the first one. So we need again to operate with an if the first clip time is over a specific value and he's in the run die state, we want to set the velocity to 0. And additionally, we want to set this clip time to the last time unit of this clip, so he gets freezed. Okay, let's do this. So here we have our pop wrangle. We will use an if expression again, and the interesting thing here, this is not a normal float, it's a float array. So to get this one, we need to use this brackets. Okay, we need to use the bracket at clip times and 0 because we want to have the first entry in the array is greater than 1.375. I figured out that that's the value we want to have to freeze, and string, the state is a string, at state is equals run die. We want to have the clip times set to array 1.375 and the second one is 0. Okay, and last but not least we want to set the velocity also to 0, so it's a vector. Okay, so that's it. Let's see if this is working. Back to the scene view and let's reset our simulation and step here to see if our new point wrangle is working as expected. Okay, that looks really good. So the die animation gets triggered as we expect, but then if the agent falls down, the velocity gets set to 0 and the clip freezes in the end. Really nice. So that's working as expected. Our agent freezes and the simulation stops looping. Next we need to set up the second state here. It's the run die and the second one is the idle die. Okay, because it has the same values here, we can just use a merge and now this also should work fine. Okay, let's call this pop wrangle freeze. Okay, so you can see animation is playing back. I mean, it's not bad, but as you can see, all soldiers have the same die animation. Also, the weapon is just not falling down. They are intersecting at some points, as you can see here or here. So I think it would be even nicer if we would switch at a random point to the ragdoll state. With this new ragdoll features introduced in Houdini 15, we can get a more realistic and more random look. So every soldier we do something unique, because if he's just running in this velocity direction, he will perhaps, if we activate it now, he will roll over the ground. The other one will just straight fall down, slide a bit perhaps, but all in a realistic way, as far as it's possible with the ragdoll. I mean, there are always some limitations, but I think we can get a more realistic simulation. Yeah, in the next lesson, we will take a look at this feature the first time, switch our agent for the dying state to a ragdoll animation. We won't replace completely our animation, because I think uh, it's really nice that they throw their arms up in the air, and I mean, that wouldn't be possible so easy with a ragdoll. So we will just switch them for this agent, for example, around that frame here. We would switch him uh, into the ragdoll state, so then all the bullet solver would simulate him completely. Then even we can make that his weapon falls down and so on. Okay, so see you in the next lesson, where we take a look at the ragdoll. Welcome back to the next lesson. Now we will take a look how we can add some ragdoll effects to our soldiers here. At the moment they are just running, and then the die animation gets triggered. But as you can see, it looks a bit similar because it's the same animation for every soldier. So I think it would be really nice to have some ragdoll be activated, for example, at this frame here for this soldier here, or at this frame for this one. So we get an individual behavior for every soldier, and so it's a more interesting look for our crowd simulation. Okay, so to do this, first we need to create some collision geometry, because we need this ground here as a collision. Otherwise, the soldiers would just fall into the nowhere. So jump back here into our scene. Here is the out beach. So it's the sand here, and now we going to create a collision geometry. I mean, the ragdoll system is working with the bullet solver, so we have a few options for the collision geometry. So let's create a new out here. Just copy this one and call it out beach collision. And for the moment, let's just add this one here to our simulation. Let's use the shelf tool up here, rigid body, static object, and go. Okay, now it should be here. Into our crowd sim should be now this new static object node. It's called scene. Let's call it ground. Like I mentioned, if you jump to frame 300, you will see the new added ground, because our simulation starts at 300. And now let's take a look at the different collision representations. So as I mentioned, it's working with bullets. So interesting here is the bullet data, and we can show the guide geometry here. So, and now you already can see the problem, because bullet is normally working with convex geometry representations for the collision. Now it just closes down our collision of the beach from the highest point to the lowest, like this, as you can see here. And this would result in really strange collision behavior. As you can see, the agents already start in the collision object. That's definitely not what we want. Um, I mean, here are some other options. You could say it's a concave object. Then it looks right. If you hide the original geometry, you can take a look. It looks all fine, but I can say that Bullet has some problems with concave collision objects. So I think we should use another way. So back to convex hull, and now we are jumping back to our geometry, and we're going to prepare it better. Jump there into the scene, and now we are going to add some more nodes here. The idea is just to create a volume out of this geometry, and then we will shatter it just roughly if, around 500 pieces. And then we're going to use this fractured Voronoi ground as a collision. Then we can use this convex option and it should work pretty well. Okay, so we're going to do an extrude volume here, but first we need to reduce it a bit, otherwise it will fracture a long time. So pull reduce, let's say 20% here for our ground. Let's hide other objects for now. Okay. Then we're going to use this extrude volume node here to extrude it down a bit. Yeah, that's fine. And next we're gonna use the scatter node here to get some points scattered. Let's say 1000 is a bit too much. Let's say 600 here. Okay, and next drop down a Voronoi fracture. Oops, sorry, that's wrong. Here in the second input there need to go the points, in the first input the geometry. Okay, now it will start fracturing. That will take a few seconds, but I mean we only have to do this once because it's all static, and then we can use this new Voronoi object. As you can see here, we can use this one as a collision. So last step, let's assemble it to create some packed objects. Okay. So just connect the out beach collision now to this new assemble node. And here we have our 600 packed fragments. Let's jump back into our crowd simulation. It hasn't updated, so you can just do a control click down here and then all objects will update. Okay, here please check the create convex hull per set of connected primitives. We could also use this packed object here, RBD packed object, that would also recognize our packed fragments. But for now it's just fine to use this toggle here, then it automatically looks which primitives are connected in your geometry and creates for every single primitive which is connected an own object, an own convex object. So that's very useful. If you have more complex objects, you can just select this option here and Bullet will automatically split it up in connected pieces of geometry. Okay, so let's deselect show guide geometry and just display the normal geometry here. Okay, so now we have our ground prepared. It's not 100% the original ground, but it should work well. Okay, so the next step will be to create a new trigger and a new transition here because we need to switch our agent to the ragdoll state. As you can see, it's automatically set up here, the state, which is called ragdoll. So we just need this trigger and transition. Okay, let's just copy this one here, for example, call it crowd trigger ragdoll. And current state duration is fine because we're going to switch from the die state into this ragdoll state. Let's point 0.3 here. So it will, after 0.3 seconds, it's going to switch into this ragdoll state. Okay, next we need to transition, copy one, and we're going to call it crowd transition die to ragdoll. Okay. idle, die, or run. Die as a input state, output state will be ragdoll as it's already created. The duration is fine, a small random time offset also. And now the last thing we need to do to check if it's working, connect the new transition here. Okay, so let's give it a try. Jump to a later frame and let's see if our agents start falling down with simulated geometry. Okay, yeah, that looks interesting. As you can see here, our agent first are in the die simulation and then the ragdoll gets activated and they're just collapsing. Yeah, that's not looking too bad. I mean, we have some strange behaviors here. I think we need to optimize our collision geometry and the constraints a bit, but the approach in general is working well. Very nice. Okay. So here also you can also see a strange issue. I mean, you have really to check the constraints, what we will do next. Another thing I just see is that the gun is still attached to our soldiers. That's also a thing what we don't want. Because if they get into ragdoll state, we want that they drop their gun and it's not constrained anymore. We will do this with a way which is also used in this limb detachment. So for now we will just use it for the gun. Okay, so next we're going to load a new constraint setup. Jump into the, sorry, not the scene, the crowd source here. And I already prepared a bit optimized setup. So just go here onto the wheel and say Soldier 01 version 3. You should have it into your scene if you use the 18 start hip. If not, you can get it out of this 18 start hip. And for the collision layer, we also going to change something because for the weapon we are using at the moment as a shape the capsule. And I think it's better to use a box shape here. Okay, let's move it a bit. Yeah. Okay, that makes more sense. I mean, I didn't change so much, but for example, the weapon now has a parent transform to the null, to the root object. I figured out that it works best for now like this, but like I already said, we're also going to detach the whole gun and break the constraint. But for now, that's fine. Let's do a test. Ragdoll sim here, frame 1. Yeah, that doesn't look too bad. I mean, just the thing with the gun, but we will take care of this later on into the crowd system. Okay, jump back and okay, back to the crowd sim. We're going to give it a try, and the next thing we would do then is to break this constraint for the gun. And take a look at, in general, this concept of breaking constraints when they reach a specific angle. And also, I think there's another problem with our ragdoll at the moment because, as you can see, the agents are running, and I mean, if they are running, they have a certain velocity with them, especially when they're doing this die animation. But for now, the ragdoll just gets activated and they lose all their current velocity and they just fall down. So that's not what we want. To have a more interesting and realistic behavior, we want to have this velocity inherited to our ragdoll system. That's a bit tricky, but we will take a look at this in the next lesson as well as breaking the constraints. So see you there. Welcome back. Now we will take a look how we can break the constraints here when our agents start falling down, and it would be good that he drops the weapon, so it's not constrained anymore to his arm. To do this, let's just do a minor change to our constraint setup again here. Let's put here 180, so minus 180, 180, so like this. Then the weapon has a few more possibilities to rotate before the constraints breaks. Think that's better to relax it a bit. Back to our crowd sim, already pre-set up are direct door constraints down here. And as you might know from other bullet systems, we have the two constraints types up here, the pin constraint and the cone twist. All this node which we use to create these constraints, which you saw earlier, already set up if it's a pin or a cone twist constraint. Also added here is a solver in which you can modify the ragdoll constraints and even break them. So to do this, let's jump in the solver here, and you might notice that if you do something in here, everything disappears, and the changes are not committed immediately. So it's always the best to do some changes here, jump back out, and then reset the simulation to see your changes. So don't stay in here, then you directly get some errors. Yeah, so let's first talk about the idea, how we want to define when the constraints will break. Because we don't want to break all the constraints, then our soldiers would lose parts of their body, a leg or a head. I mean, like I said, the system you can use for this limb detachment thing, but that's not what we want now. Also, you have to keep in mind, if you use it for limb detachment, that you need a special layer for your models, where, for example, if you want to detach the leg, then the mesh needs to be separated from the beginning here, or you can switch to this layer then, because otherwise the primitives which are in this region here would stretch endless if the leg flies away, for example. So, but for the gun, it's perfectly working because it is already a separate mesh. So, okay, let's take a look at the geometry spreadsheet up here again. I mean, it's a really useful thing to see what's going on. We have our crowd object here. Take a look at the geometry. Let's get some space. And especially if you go in here, you have a lot of attributes. So for example, on the points of our constraint, we have the name. So this defines which constraint is which part of the body. So for us, interesting is the weapon constraint down here. So this point is the weapon constraint, and for every point is a primitive in this case. So here on the primitives, we have a lot more attributes which we can use to define when the constraint should break. So for example, let's step a bit further where the first ragdoll agents get activated, because then here will appear a few more constraints. Yeah, like the angle, for example. This one is interesting. It defines the current angle of our constraint, and we can use it to say, for example, if the angle is more than 0.5, then our constraint should break. Another thing here is the distance. That means how much the constraint is violated at the moment. And there are some other attributes we could use as well, like the force or the torque, for example. So the first thing we're going to do is to use an attribute promote here um, to see this name also on the primitives. So let's do an attribute promote like this, and then we're going to promote from point to primitive the name attribute, and let's change it to new name and don't delete the original. So let's call it p point name, now this attribute should be on the constraint primitives. And as you can see, yeah, here it is. So p name. And now we can see for which is the primitive, which is our weapon constraint, for example. So to delete the constraint, we are just going to use a primitive wrangle with a remove prim expression. So basically we are using an if condition. So for example, if the angle of our constraint is more than 0.4, then the prim will be removed, which is a constraint, and the weapon can fall down. Now the problem is that we have several constraints here, and for example the constraint of the head has an even higher angle, and if you would just say all constraints with an angle higher than 0.4 should be removed, then our soldier would fall apart. So that's also why I promoted this name to our primitives, because we are doing two conditions for our if expression. So first, if the angle is higher than 0.4, and second, if the name is weapon. So only the weapon primitive constraints get affected. To have it a bit easier, because at the moment here the first part of the string attribute is always refers always to which agent it belongs, we are going to use another really useful node, which is called attribute string edit. And here it is. Just put it here. And so let's say from the primitives we want the p name. Then here in the editor you can work with wildcards, which is really useful. So let's say from wildcard weapon to just weapon. Okay, let's see if this is working. Whoops. And yeah, it works perfectly. You can see now all where before the soldier was in the name, now only is called weapon. And that's exactly what we want for our remove expression. So back to the primitive wrangle, we are going to use this if expression here. If the angle is bigger than 0.4 and if the p name equals weapon, whoops, we are going to remove the prim where this condition is true. Remove prim. So geo self whoop whoop at prim num and 0. Okay, very nice. That should work. Okay. So, like I said, let's go back, don't stay in here, and back to the scene view and reset the simulation. Okay. Let's take a look if our expression is working as expected. Let's see. So, no, they're not dropping their weapons. So let's jump back to our constraints and take again a look. Also really useful thing I think is if you do a right click here, you can just open up the spreadsheet, and then you get all attributes here into this new window, which is perfectly if you can move it to a second screen. But for now it's also fine here, and now you can jump back and have simultaneously these attributes here and a simulation, and you can see how the values change here. So let's investigate a bit more why the weapons are not dropping. Let's point here angle and the p name to see what's going on. So just sorted here that we just get our weapons, and as you can see the angle of our weapons is really low of the constraints. So I think it's better to use another attribute, which for example is the force. So as we see, yeah, the force values are really high here. So let's just use the force instead of our angle attribute. in the solver here. Okay, so let's put here force, and let's say if it's more than 50, then the constraint should break. And once it's broken, it won't return, so because it's deleted. Okay, let's go back, reset the simulation, and let's see if we are more successful with the force attribute. That's often the case that you have to see which attributes works best for the situation. And yeah, that works as expected. Now our agents drop their guns, and because they get a heavy impact, some are really flying away, but that's fine for now. We will tweak it more when we transfer this velocity. So for now, I think we were successful with breaking the constraints. As I said, you can also use this for limb detachment, but for us, the next thing we are going to do is to set up this inherit velocity system, which is a bit complicated. So let's do this in the next lesson. See you there. Welcome back. Now we will take a look how we can inherit the velocity of our running agents to our ragdoll sim in the moment where they get activated. As I said, it's a bit complicated because we are running into some issues there. First thing is there is no button just to inherit the velocity. So we need a way to save us the velocity of our agents, but we need the velocity before the ragdoll gets activated. Because in the moment where it gets activated, they have this ragdoll velocity. So we need to save us the velocity on the last frame where it's over 0 and the soldiers are still not active. If we take a look at the attributes here, you can see that at the moment, at frame 429, no agent is active. That means that no agent is at the moment in the ragdoll state. If we go on, we see that agents get activated, and in the end, all are ragdolls. So let's take a look here just at the attributes active and velocity. Okay, so active 0, here we have our velocity, and as you can see, the agents get activated and velocity gets to 0. So we just want to save this last value of velocity to transfer later on in the ragdoll, so in the bullet simulation. To do this, we are going to create a solver here. It's like the same, the SOP solver, it's the same like down here with the constraints, but here we're going to put it into the multi-solver because we're going to modify this all agent attributes and not the constraints. So let's get a bit space, and here we have our SOP solver save velocity. And in here, we have our dot geometry. Like I said, again, if you're inside here, there are some issues. So at the moment, you cannot see any attributes anymore, but we know what we want. So let's drop down a point wrangle here. Point wrangle. Okay. And like I said, we want to save the velocity, so we're doing an if expression if the velocity bigger than 0 and at active smaller than 1, we're going to create a new attribute which is a vector, and we are going to call it velocity, so v old, and say only on this frame we're going to say it's the velocity, current velocity. Whoops. Okay. Yeah, that should work. So Don't ignore these warnings here, just jump back, resimulate, and now we should have our VOld attribute. Just put it here so we can see it. And it constantly saves the velocity, but important is when they get active that it stays with the last non-active velocity value before it goes on. Yeah, that looks like it's working. As you can see here, this one has still his velocity because it's not active. We go on and the last value of velocity gets saved before they get active. So that's exactly what we want. And also important here is that we set this condition only save it if it's over 0. Because of some reason they get 0 a few frames sometimes before they get active. And we want to have the last value where is velocity. So it's perfectly working. And we're going to use this velocity old value to inject into our ragdoll simulation. Perhaps you already know from bullet simulations that you can also use all the pop forces. And in this case, we are going to use a pop wop, which we also just plug in to the multi-solver here. Okay, in here you have access to all the attributes that drive our agents. So for example, velocity, force, age, and so on, like with normal particles. So what we're going to do in here is that we want to add the VOld to our current force so that the bullet ragdolls gets influenced. So we have to think about a few more things here because we don't want to add it constantly after the bullet gets activated. We just want to inject it once on the frame where the agents get active. So if we just would do here an add, let's pick the force, pipe it through so it's get back into the system force. Then we using the bind to get our VOld attribute. VOld, okay, it's not a float, it's a vector. Here it is, and yeah, let's see what happens. We plug it in here. You can see now we add the VOld constantly into our simulation. So let's see what happens. But before we do this, an important thing I noticed is that the order here is quite important into the multi-solver. So otherwise, it could happen that the pop wop here not influences the bullet simulation. Instead, it would influence the particle solver in the crowd solver here, which is here in the end, the pop solver. So let's make sure that the order is different. The bullet solver should be above the crowd solver. Yeah, like this. So now it should influence correct. Let's jump back and to a later frame to see if the velocity injection works. Like I said, now it should inject it constantly on every frame, so our agent would get pushed around. Let's see. Yeah, they don't calm down, so it looks like it's working. We will going to add a multiplier there because I think we need it even stronger. So back into the pop wop. Here we are going to drop down a multiply because we want to multiply our VOld velocity with a constant value here, or just say promote parameters so we have it up here. Okay, but make sure that it's not in float, it should be in vector because we have the VOld is also in vector. Okay, let's put down just for testing 250 for example, 250, 250. And let's play again the simulation and see if now we see an stronger impact on our agents. Yeah, that is exactly what it should do. So the v_old velocity vector gets added on every frame, so our agents start flying here. Yeah, very nice. So how it's possible to say that it just gets injected on the first active frame? Normally in SOPs you would use also a SOP solver to just save this frame where it gets activated. But if we take a look here at the geometry spreadsheet, we have also a few attributes which will help us, like the creation time, for example. It's -1 when they are not active and get switched to this time where they were activated or created, in this case the bullet objects. And I noticed that they are already active when the creation time is still -1, as you can see on here. If you take a look at this agent, we see creation time -1 and active is already 1. And then one frame later it's switching to the creation time on which the bullet agent was created. So we can perfectly use this relationship of these two attributes here to say if the creation time is still -1 but active is 1, we are going to inject this velocity here. Okay, to do this we need to drop down a few nodes. Let's get some space here. First we're going to use a two-way switch, and then we need to get this creation time attribute, which is a float value. So put here creation time, okay. And we're going to compare this creation time, going to compare this creation time value with a constant value compared to float, in this case -1. And we're going to see when it's equal to -1, using this as a condition here in our two-way switch. And then we're going to get two constants here. Okay, and the first one is just 1, the second is 0, that's fine, because now we are using these numbers here to get multiplied with our v_old velocity and our strength multiplier. So let's connect it, and now if the system is working, it should compare if the creation time is -1, and if it's -1, it should multiply this value here with 1, so that means that it gets fully injected as a force. And if it's not -1, which is one frame after it's activated, then it would just be multiplied with 0, that equals 0, so no more force here. Okay, so let's jump back, reset our simulation, and let's see if it's working like expected. Once more, we saw that here the geometry spreadsheet is really useful to see what attributes are already there to work with, which are really a lot when you're working with crowds. So let's see. Yeah, that looks much better. I mean, the weapons are still flying, but our agents get activated, and once this force push, as you can see here on this agent, for example, or this one here is spinning around, rolling over the ground. This one here as well. It's not just statically falling down, but I think we can optimize it a bit more. So let's take a look at this random time offset here and put it to a smaller value. And one more thing is the trigger here. This one we also have at a lower value, so 0.03. So they get a bit earlier in the ragdoll state. Otherwise they are just already fallen down with the animation, and that's not what we want. So simulate again. And yeah, that looks promising. Yeah, that looks much better. Now they are not stopping, they are just getting activated. Perhaps our force push is a bit too much on some agents, but it's looking way more dynamic than before. Yeah, very nice. And also with the guns which are detached. Okay. Yeah, that's exactly what we were looking for. So, as this is working pretty good, I think we can go on, and in the next lesson we will set up our defenders, and after this we are going to create some grenade explosions, also using the ragdoll systems to get our agents flying. See you there. Welcome back. Now we will take a look how we can set up some defenders that will be up here. Uh, there should be already a geo container called defenders, and so just enter it. And now we will paint onto our beat geo just where we want to have our defenders. So create an object merge and get our beach here. Scene out beach. Okay. And let's template this here that we can see it and just show the beach. And before we start painting, I would like to blast all this part here because we don't need it and it will just slow down the painting process. So blast, and remember here you can also use the syntax. Let's say when it's bigger than 22, then it should be deleted. So just hit delete none selected, and now we stay with only this stripe here. Okay. Next, drop down a paint, and we just assign a black color here and paint where we want to have our soldiers stand. Just template this that you can see where the barriers are. I use a slightly bigger brush size here. Okay, it doesn't have to be so exact, and we also want to place some in here. Okay. Yeah. Okay. Don't have to be too exact, just to have some defenders. And remember, you can always add more later on if you just paint somewhere else. It's all procedurally set up. Okay, paint is finished. Now we want to use the scatter again. And let's say density attribute here, the color. And let's say we want to have 50 defenders. Yeah, that's nice. And yeah, the relax is fine here because we want to have them stand a bit separated. Okay, last but not least, create the out and call it out defenders PTS. Okay. Yeah, very nice. Now we have the points for our defenders, and let's jump to the crowdsource, and in here we can use another crowdsource to bring in our defenders and have them be a separated group. Okay, so merge the points that we just created. Uh, defenders out defender points into this object, and then we just gonna copy this crowdsource here, and the agent input is fine, but in the second input we want to have our points. Okay, that's nice. Now you already see some agents here. And now we're going to merge our two crowd sources together. Just move everything a bit down here, drop a merge, and that's it. Okay. So we want to have a difference here. Let's put here group name defenders, and the rest should be fine at the moment. Or let's check. No, they're heading in the wrong direction. If we ghost the other objects, you can see that they're all looking in this direction. And for sure, we want to have them look at the attackers here. Okay, so that has to do with initial velocity. So put here -1, and now they're looking in the correct direction. Very nice. Okay, this is the other crowd source. Now we combined the two, and now we just need to create some more triggers and transitions in our crowd network. Let's take a look. Jump back. Just for the scene, make sure you see the merge down here. And for our defenders, we don't want to see the points, we want to see the geometry. If you jump into the crowd source and let's display our simulation here. Now you already see that the soldiers are already in the simulation because they are it's grabbing just the last output here. So jump into the sim and let's play it back a bit. So our defenders start moving. That's not what we want. So let's change the first state in which they start. Here it's at the moment idle, and we just want to have idle shooting. Okay. Back to the simulation, just reset it, and let's see what's happened. Now they should stand there and already switch into the other state. Yeah, that's nice, because we already set up this transition. If they're in the idle standing state, then they will switch after a few seconds into the crouch state. That's why the soldiers here start crouching. Next, we want to add some triggers that are special for this group. And also we want to have a new stage, which is called throwing grenade. So some of these start randomly throwing grenades at our attackers. But how to do it? Let's switch it to the next lesson. See you there. Welcome back. Now we're going to add this new trigger and state for the grenade throw action for our defenders here. To do this, let's create a new group because we don't want to have all the defenders throwing grenades. That would look like a bit strange. We just want to have, let's say, 10% who do this. So let's get some space here first. It's all a bit close together, okay, because also we're gonna add more states in a few seconds or minutes here. Okay, just move it here. And in this stream here, we're gonna add our new group. We can just copy the group up here where we created the sandbags, and let's drop down it here, call it pop group grenades, and let's say 10% is a chance to get into this group, and the source group is defenders. So just the ones who are in the defenders group can get into the new group, which is called grenades. Okay, very nice. Now we need the new trigger and transition here, because in this case we also want to have the end condition again to check if they're in the group. Let's just copy this nodes here, and you can already connect them. we want to again have a current state duration, let's say of 1, and here we need the group check, so it's called group grenades. So only if they're in the group, the trigger will be activated. So let's call this here grenades group check. Okay. Okay. So now we want to switch from the idle shooting or idle crouch to the grenade throw state. Duration 0.5 is fine to have a bit smoother. So last but not least, we need to create a new state here. Just copy one with a static attribute and connect it. It's called grenade throw. Okay, so let's jump back to check if all the changes are working as expected. And then the next thing we would do is to take a look that our soldiers stand up again if they are not in the grenade group, but already crouching. Okay, let's see. So they're going all into this crouch state. And now something else is happening. Let's see. Yeah. Here you can see 2 of our soldiers who start throwing the grenades. That's exactly like we want, but as I said, we also want the other ones to stand up again, and these 2 guys here should stop at some point and also go into another state. So let's drop down one more transition here. Let's see, copy these 2 here because again we want to current state duration, let's say 2 seconds, and here the transition from idle crouch to idle shooting again, so that they stand up again or stop throwing grenades. So also grenade throw. Okay, let's connect the state, reset the simulation, and now with just a few states we should have way more interesting behavior for our defenders. There also might be one more issue we need to fix, because as you remember, we said that there is this live attribute and then we have this attribute transfer, and at some point the agents start getting into the ragdoll state and the die animation. So let's see if this happens here too, then we need to fix this. Yeah, here the 2 guys are standing up. So here's already this strange behavior, and I think that's because the ragdoll is activated. Let's step back and see that we don't transfer the live attribute so fast on our defenders. Back into the crowd source. We're just going also to separate these 2 groups and use 2 attribute transfers. So for example, we can say that the defenders don't die so fast. Let's create a group node here. And I think one of the easiest way to get the points which are in the first crowd source is just to do points, let's call it soldiers, like the soldiers in the first group are called. And then we're going into group by range, and normally it's the number of points which are here, so that would be all of our agents. But there's also this n points expression, number of points of a specific group. and or node, and we wanna point it to the first crowd source. Okay, so like this, and then -1, because otherwise we get one more point that we don't want. Let's say 2 of 2. And if you take a look now, we have 9 points in soldiers and all in all 59, because we have 59 defenders and just 9 soldiers which are attacking at the moment. Okay, very nice. Next, drop down one more group node. In this case, we don't want to use all these here. We're just going to use a combine. Let's say defenders unequal soldiers. Okay, now, yeah, we have 50 points in defenders and 9 points in soldiers, exactly like we want. And again, it's procedural. If you update some numbers here, it will just continue working. This first attribute transfer now will be for our soldiers. So let's pick a destination group and make sure you switch here to points. And now we're going to put this transform down here because we want to have 2 transforms. One which is way slower and the other one which is fast for the soldiers. Again, just copy it down here so we don't need to duplicate the whole stream. Copy the attribute transfer and just put here our defenders. And we have this animation curve here. Let's stretch it out a bit and let's start it later. Like more like this, that the defenders don't die so fast. Okay, and connect it here. Very nice. So this one is attribute transfer soldiers and the other one is for defenders. Okay. So that issue should be also fixed. Let's jump back, reset the simulation and give it a try. Okay, there's still an issue, and so let's check the transition again. Yeah, here's a space. That's already the problem, I think. So delete the space here and simulate again. And we will see if our soldiers and agents then start doing what we want. So throwing grenades, switching to the crouch state, standing back up again, and so on. In the next lesson, then we will take a look at one of the most interesting parts, adding grenade explosions and then having these influence our soldiers, so activate the ragdoll again and let them fly through the air. Yeah, but for now this looks much better. They stand up again. There are a few who get the ragdoll triggered, but not as many as in the in our attackers here. Yeah, that's really nice, like we want. So I think this lesson is finished. And we're going to take a look at the advanced ragdoll effects in the next one. See you there. Welcome back. Now we will finally take a look how we can set up the explosions that we use as in a ragdoll system to blow up our agents. In this lesson we will more look at the procedural generation of the explosions and the placement, and in the next one we're going to dive into the ragdoll stuff. So if you want, you can skip this lesson and just continue with the setup explosions in the next one and then look into the ragdolls. But for now we just start with the explosions here. Here is our test group, so we want to make sure that here are also some explosions. So I was looking for a procedural way to place them and to have the possibility to add more later on easily. So I think the best thing is first to define a rough area where we will scatter some points. Onto these points, explosions get copied, and we can grab these explosions as well for the triggering of the ragdoll effects. So let's drop down a geometry node here, call them explosions. And in here we will merge our beach. Oops. Our beach here in an object merge. And then we are going to paint the rough areas. Okay. All black, bigger brush, and now we are going to paint. For example, like I said, we want to, for our test group, we want to have some explosions here, also at our defenders. And with this system, you can always add and remove explosions. It will be really easy. Okay, some here. Okay, that's it. And now we are going to scatter the points on which the explosions will be copied in a few minutes. Let's use the density here. Let's, for example, point 0.3, and we're just going to use the white areas we just, the white areas we just painted. Few too many explosions. Let's do it like this, or even less. Okay, that looks better. So now we have our explosion points, and for sure to copy something on them we need an explosion. For now we will just create a simple proxy explosion, but later on it would be also really easy possible with the system to copy some pre-cached pyro explosions. But for now a sphere with some noise has to be enough. Okay, let's shape it like an egg and move the center up, because we're going to copy it and scale it later on. Yeah, now we have many eggs here on the battlefield. Let's drop down a mountain to get a bit more interesting shape. Sorry, for sure we have to use a polygon mesh 24 and perhaps reduce the height a bit, so like this for example. And I mean, we could also copy stamp these values here to get a more unique explosion, but for now I think it's fine like this. And now we need to set up some more attributes, like the p-scale attributes that will be read by the copy swap here to scale up our explosions to have the feeling of this impact. So drop down a point wrangle. Okay, now here we're going to set up a ramp for the p-scale attribute, so we can use this control ramp to scale our explosions. To visualize a bit better, let's use just the point color attribute here. So vector at cd is equals a channel ramp expression, and just call it palm. And as a lookup, we're going to use the random points, the point number ptnum, and close it. Okay, that's working, and you can use this really handy button here to let Houdini create you the just created parameter, which is a ramp in this case. And now it's necessary to set the p-scale, so let's use add p-scale and equals the color, but we are also going to do a fit because we want to have our explosion a bit bigger, and this ramp is just from 0 to 1. So let's use one component of the color, and let's fit it between 0 and 3. Okay, very nice. And now, as you can see, our explosions already reacted, and we can control them with this ramp here. Okay, next thing is we need some animation for this ramp, but we don't want to do this manually. So I think we can use an expression here as well. Just select one of these points here. We are going to use the $f expression here because we want to have it move over time in this direction to trigger all the explosions. For sure we need a small offset because we want to have started at frame 300. So let's point here, let's say 1.55 minus $F divided by 500 so it doesn't move too fast. Now, as you can see, oh, explosion is still running. Let's cancel the explosion and deactivate it. But as you can see now, this point here is moving as we progress with the time slider. And for the first point, we want to have the same, just a bit earlier. So we have the smooth fall off here because the first point defines a 0 scale and this is the highest scale. So this ramp here will be the time in which the explosion is growing. So as you can see now, the explosions start growing and then they stop. To get rid of them when they are 0 or already exploded, we're going to use a blast, drop it down, select points, and then let's say if at p scale is smaller than 0.2 or if p scale is bigger than 2.99, it should be deleted. So you get an error here or a warning, but we can ignore this. The explosion should be removed now. I think we have to activate on the copy stop that all the template point attributes from here will be transferred onto our explosions. So yeah, now it's working. They just appear for a few frames, explode, and then they disappear. Just let's remove the alpha attribute here because we're going to use it now to give it a bit nicer look, even if it's a proxy explosion. So just copy this expression here, down here, and let's call this here alpha and invert it because we want to have the most opaque explosion when it's small, and then when it starts growing it should get more transparent. Okay, yeah, like this. And I also prepared a shader already here in Shops. If you open up the scene file, you will find it, explosions. Let's just assign it to our explosion here. And then it will look even a bit nicer. Okay. As you can see now, our explosion, for example, this one here, starts and then when it is before it disappears, it's get more transparent. Okay, so now we have a really procedural way for our explosions here. Like I said, you could also do this with pyro caches, but for now it's fine like this. In the next lesson, we are going to use these explosions as a trigger in the Ragdoll system. See you there. Welcome back. Now we will use the recently created explosions as a trigger for some really cool Ragdoll effects here. To do this, dive into the crowd system, and at first we need a new trigger and transition here. I think we already have a ragdoll, so let's just copy this one here, drop it down. But now we don't want to use the current state duration. We want to use the object distance point cloud in this case, and SOP data, and use the explosions we just created. Okay, we have no out here, that's not good. It's always important to have this out node. That will reduce the errors in the progress. So let's drop down an out node here. And also I think it would be good to scatter some points on our explosions because we're going to do a point cloud lookup in the DOP later on, and for this it's always good to have enough points. So out, let's call it just out, and we will display this node, but for the simulation we're just going to drop down the scatter here, and let's deactivate this, let's say 10,000, and now there should be always enough points. When it gets interesting here, yeah, now we have enough points on our explosions, so the lookup will work. Let's jump back into the crowd sim, and now we can select here our explosions out. Let's say this first deactivate simulations. Let's say search distance 20. The comparison distance can be really low. Let's say 3 meters. And now we need to transition. In this case, it's more the run and run shoot for now, which should translate into the ragdoll. That's fine. Duration, we want to have it directly on the impact, no random time offset because it's an explosion. Crowd transition explosion to ragdoll, crowd trigger explosion. Okay. So let's just connect it and see if that is working. I think for now we should just deactivate our other ragdoll trigger just for a moment to see the correct results here. Jump back, activate the simulation, and just step until a further frame where this one explosion here should hit our test agents. Okay, let's see what is happening. Now the explosion happens and that's not looking like it's working. Let's check. Here it's a run shooting is the right state. So I recommend pick it from the list and it's you will avoid these problems. So let's jump back and for some performance reasons, let's just go into the crowdsource and for now get rid of the defenders. Okay, now we just have our test agents and it will be a lot faster. So now the state should be right, run shooting. And let's jump to a further frame to check if it's working. Yeah, that looks much better. Now it looks like that nearly all agents here were activated from this explosion to switch to the ragdoll state. So the next thing we want to do is to create a new force that pushes the agents up in the air and away from the explosion. I think you can remember what we did with inherit velocity earlier. So we used this pop-wop here. Let's call it pop-wop inherit vel. And what's going on? Oops, no, don't change the output flag. And now we are going to use another pop-wop just to create this force which is pushing the agents into the air. So drop it down, pop-wop, and connect it. Let's call it pop-wop explosions. Okay. And in here, we are going to use a point cloud lookup. So use PC open to get the information of the points of our explosions. So promote this file parameter here and position is the position of our points. And in the end, we're going to add it to the current force as we did with the inherited velocity. And here we do the PC filter to get a specific attribute, which is force in this case, and add it to the current force. Perhaps you remember we don't have a force attribute yet on our points of the explosion, so we will create it. Jump back to the explosions and before the scatter just drop down point warp, drop it down. Let's jump in and let's just use the normal direction as the normal and the force. Also, we're going to add a constant value here. We can define on one level up, so promote a parameter and make sure it's a vector here. Vector, okay. So now the force attribute will be there and we can also just add something to it. Let's visualize it. Freeze simulation for a second. Let's see where the explosion here happens. There it is. And if you display the normals now, oops, sorry, the normals, you should see that it's looking like this. I mean, that's nearly what we want. It pushes outwards. I think it would be good to have them get pushed up in the y-axis a bit more. So we are just going to add a value here of let's say 0.8. Make sure you are also connected to the normal so we see it better. Okay, now it's exactly what we want. It pushes up and a bit outwards, and the scatter points will get this information also. So, but set the display flag just here, and the out will get the correct values. Back to the simulation, we need the correct path to the point cloud texture, and I mean we could write them out, but I think it's easier because we will do a lot of changes just to use the op expression here. Op object explosion, and it's called just out. Okay, that should work. Now the information from these now the information from this out node will be fetched and used as a point cloud texture. So we already set it up, PC open, it filters the force and adds it to the current force. I think here we will also need some multiplier. Okay, just promote this one here, make sure this one is also vector so we can influence all directions separately. And I would say we have to push this, so just start with, let's say, 200. We want to push it more into the y up axis, so 900, 200. And just jump back, start the simulation again, and give it a try. Okay, I think we need to do some more changes here. Here's a spelling error. It's explosions, and inside the force we also need to set this radius, this search radius, let's say to 5. Okay, 100 points, and give it a try. So let's see if our soldiers start flying now. Yeah, that looks much better. I think we have the force a bit over exaggerated now, but as you can see, it's working like it should. When the explosion gets triggered, our soldiers get blown into the air. Very nice. So I think we have a good start point here for more advanced ragdoll stuff. In the next lesson, we will take a look that the explosion just affects the first few frames with the force, because as you can see here, it always looks a bit unrealistic if the force is active for, let's say, 10 frames or something. So I think it will look much better if we just activate it on the first 2 frames, and then it's not active anymore. To do this, we're going to do some changes to our explosion, the expressions we used there, use a force multiplier. Also, we are going to do some general tweaks to our forces here. Okay, see you there. Welcome back. In the last lesson, we were successful with our ragdoll explosion here, as you can see. But as I already mentioned, we're going to make some tweaks so that the force is not constantly active when the explosion is there, so to get a better effect. Let's go back into our explosions here, and we're going to take a look at the wrangle here. So let's just display it and show the geometry spreadsheet. I think here's a good place to create this force multiplier we are looking for, because we can say, for example, if the p scale is in this range, we want to set this force multiplier to 1, and then down here we can multiply it with the force. So let's create this and say if the p scale is smaller than 1.3 and p scale is bigger than 0, we want to set this float attribute we call force mult, set it to 1, and else we wanna set this force multiplier to 0. Okay, very nice. Now let's take a look. Here's our force multiplier. It's at, for this explosion, for example, it's at 1 when it starts, and when it's growing and growing, expanding, at some point it gets back to 0 before the explosion is gone. That's exactly what we want, and here in this point warp we can already use our just created point multiplier to multiply the force value here. So let's bind it. Force mult. Very nice. And use this as a multiplier here. Okay. So as you can see, this just changed. When the force multiplier is 1, force is also has a value, and then it's 0 again, and force is also 0. That's like we want. Very nice. So let's jump back and give the simulation a try. Jump back and resimulate. Let's see if that affects it like we expected. Okay, let's see. Yeah, that looks much better. The explosion starts, it affects our agents, but not as exaggerated as in the previous version. So the force just is a few frames active, and then it gets back to 0, and the gravity can do its part. Very nice. Okay, so as I mentioned, we going to do some more tweaks to the general ragdoll system here. We're going to just switch back on our switch for the die animation to switch it to the ragdoll and do some tweaks. Let's lower this time here, because I noticed in some situations the transition is too long, then the agents are doing nothing. So let here also get rid of the random time offset and set this transition to 0. I would recommend setting these to all ragdoll states you do. And then here for the transition, we're going to lower the time offset a bit, and also the duration, because otherwise it's still in the transition from the idle shooting to die, for example, but then because the transition is not finished, there's a problem switching to the next state. Then there's one more thing we need to do, because I also noticed that with this setup, we also use this inherent velocity when we ragdoll the explosion ragdolls. Then they all get a push in this direction because it was their velocity before the ragdoll was activated. So we are going to use this point cloud as well here. So drop down a PC open as well. Promote a file. Oops, sorry. Promote a file and get P as a position. So same search radius as in the other one. PC filter. Here we're going to use again this force mult we just created. So it's a float, and we're going to multiply this inherent velocity system with our force multiplier. That means if our force multiplier is 1, then this system should be 0. So we're going to use an invert, or like it's here in Vex, it's a complement, to invert this value and multiply it. So like I said, if our force multiplier is 1, we will switch it to 0 to multiply it here in the system. So no velocity gets inherited if the force multiplier is active. If not, if the force multiplier is 0, here will be get out a 1 and the system will still work. So for the normal ragdoll die animation, it will work, but not for the explosions, it will be deactivated. That's exactly what we want. Okay, jump back. Let's take a look. Everything is back in place. The ragdoll is connected. So let's give it one more try. Okay, here we are. Yeah, now it works as expected. Some also fly in this direction. And I mean, now all get hit by this explosion, but the ragdoll should also be in place. Ah yeah, as you can see here, one is not hit by the explosion, and then the ragdoll gets activated and he falls over. Okay, very good. So as we have implemented this ragdoll explosion, slowly we get to the end of this course, but for sure we shouldn't forget to take a look how we can cache this whole simulation out the most efficient way, and take a look at some rendering stuff, so how we can get easily some variations. So yeah, in the next lesson we first going to get back all our agents, defenders, attackers, and see if everything is working, and then we will cache it out for rendering. See you there. Welcome back. In this lesson we will switch back to all our soldiers here and do the last tweaks in the simulation. So let's do this. In the crowdsource we just have to switch off these two nodes here we marked in red, because one is blasting all the other agents, and this one's a time shift because we said we want to start at 300. So let's bypass these nodes here with the yellow flag, and then we want to put back in our defenders here in the crowd source, and we want to switch back the start frame to 1. Okay, let's see. Yeah, here are our soldiers, our attackers. The defenders are also there. The boats are missing, so let's hit out render here with our display flag, switch back, and yeah, now let's step a few frames through the simulation, and then we will fix an issue I noticed, because at the moment we have two crowd sources, and then there's a name conflict in the constraint network. So we need to edit the agent names of one of the crowd sources. Yeah, that works. All agents are moving. Here they are shooting. Yeah, you will notice it when the explosion starts to blow up, because then one group of our agents, either the defenders or the attackers, will react really strange. Everything gets stretched, and that's because the constraint network has an issue. So to identify the issue, let's go into the crowd source and take a look here at our two crowd sources. I mean, we defined two separate groups, but the names are the same. So let's take a look. Geometry spreadsheet, and let's focus on the name attribute. So here you can see it gets the name of our agent, and because both crowd sources are using the same source agents, they get the same names. So at this crowd source we have a soldier 2 underscore 0, and here as well. So that's causing the issue here in the agent constraint network. And but there's a really easy way to fix this. Let's just use this really useful node attribute string edit, drop down it here, and we want to edit the name, and here as well, and the primitives as well, the name. And in the editor now you can say how to edit a string even with wildcards. That's really useful. So no need to use expressions here. You can just use this node. So we want to filter the soldier wildcard. And now you can see all names are empty because we haven't input something here. So let's call it defender soldier. And then it will insert again the stuff which was behind the wildcard. So that's working really good. Here you can see now the number is attached back again with the new prefix. Exactly what we want. Now if you look here and here, they have different names, and now everything should work fine here in the constraint network. Okay, back to the scene view, reset the simulation. Okay, perhaps you will increase the cache amount a bit, because after this cache amount is reached, it will start deleting the first frames in the memory, so you cannot scrub through. So let's put here, depends on how much RAM your machine has, let's say 15 gig maximum. Okay, so now let's simulate until, let's say, frame 600 here, and then we will set up all the stuff we need for rendering. So we will create a ROP output and take a look at two different methods to save out our agents, because one way is to just save the points with an external reference on the points to the agent on the disk, which I would always recommend because it's really lightweight. The other way is to embed the agents in the cached out geometry, which will create really big files. Depends on how many agents you have, but normally the other way is much better if you are sure that you have your agents directory accessible. So let's take a look when it's done here. Okay, the simulation is done. Let's take a look. That looks good. They're running, the grenades are exploding, they get blown in the air. Yeah, that works as we want. And now, as I said, we can take a look at the way to cache them out. Back into the crowdsource. Here they get back in SOP level from the simulation. So we will drop down a ROP, ROP output driver here. And with this, we will save the agents to the disk, so we don't have to cache them every time again, and for rendering. So it will automatically save it in the geo directory. I think that's fine. Let's just use the $OS as also as a folder, and then again as the file. Okay, like this, and call it soldiers. Okay, now it will write it to project files soldiers, and $F is for the current frame. Let's say we want to save out 1000 frames. Okay, and before we hit the save to disk button, which will take some time, let's take a look again at the external referencing. So here on the soldier, on the agents, you have this option, keep external reference. If this is enabled, Houdini will just write out the points with reference to the agent. So the cached out stuff is basically just point data, which is really lightweight and fast to load. The other way, if you disable this here, it will write the agent definition in the cache file down here, which will create bigger cache files and takes longer to load. So I think this is a better way. So let's just cache it out, save to disk. This will take some time, and in the next lesson then we will take a look how we can load it back in and set up some cameras, take a look at the shader overrides, how we can make our agents more individual by using the style sheets, and then finally rendering some shots. Okay, see you there. Welcome back to the last lesson of our course. Now we will take a look at the rendering and varying some materials. So when you open the scene file, the 27 start, you will find some cameras and also set up material for our soldiers. I mean, you can also just copy the nodes into your current scene. Um, so first, let's load the cache that we saved out in the last lesson. So create a file node and let's pick the cache geometry soldiers, and here it is, 1000 frames we cached out. Okay. Now you can see these are just points which were cached out. I mean, one frame is about 1.86 megabyte. So all the agent data is not saved into the file, it's saved on the disk and it's just a reference. Now we can scrub through and it's really fast. In comparison to Houdini 14, they optimized it a lot. So let's take a look. Like I said, I prepared some cameras. One is moving here a bit. Another one is a top view, like this one, for example, also has a slight animation. And then we will also create an agent camera, which is a feature in Houdini 15. You find it here in the shelf, crowd, and then agent cam. Now you can select an agent. Just select one here, for example this one, and hit enter. Now the agent cam is created, and if you look through, you will see from the view of the agent, which is a really nice feature. But for sure you have to pick the transform name, for example the head, and then offset the camera a bit, because otherwise we are inside our agent. So yeah, for example like this. Or if you want to have more a first person view, then it would be like this. Yeah. Okay, perhaps a bit up. That's nice. So now we have our cameras, the agent cam, and the next step would be to assign a material for our agent. So let's select our crowd source and just pick the material I prepared. Basically, it's just a mantra material with mantra surface with some texture and yeah, just basic settings. So select it, and now you see our agent has a texture on it. For the weapon, we would need a separate texture, but for now it's just interesting how we can get some variety into our materials here. So in Houdini 14, it was also possible to use style sheets to customize the materials per agent. It was a bit complicated, and now in Houdini 15, it's much easier. Um, you can jump here into a new tab and display the data tree, and there you can choose the material style sheets. So in this view here, you can easily customize all the style sheets for your objects. So no need to write code or something. So here in our crowd source, we want to have a new style sheet parameter, and in there we want to have a new style. And here now it's possible to define a target. So which geometry in our geo container should be affected. So let's add a target. Now we can choose between different options. For us, the primitive is fine. And now you could also set a target from the viewport selection, which is really comfortable. But we want to have some texture variation for all our agents, so we're going to use a CVEX script. Let's set up this CVEX script, put an override here, so add override script. And yeah, material parameter is fine, and it's not an inline script, it will be a script from shop. We need to create this script, but just for now, the override name here, now we can also pick it really comfortable. Just now you can see your materials you have in your scene, then you open up the soldiers material and search for the diffuse color map. So it should be here somewhere. Yeah, diffuse color texture, it's this one. Now we have a style that will affect the diffuse color texture on all our primitives, so all our agents. Yeah, now we need the script to get some variation. So let's jump into the job level and create here our CVEX shader builder. So let's call it random texture. Okay, jump in. And now we are again in the wax context. So we know that the attribute is called diffuse color texture. So let's bind here an attribute which is called diffuse color texture. Okay. and it will be a string. So let's select, string. Okay, then we need some wax snippet here. Drop it down. And now we need an attribute which we can use for the data binding. So to define on which attributes the randomization should be based. So that will be the ID attribute. Let's call it ID, and it's an integer. Okay. Very nice. Now plug both here into our wax snippet. And then we need a bind export again from the diffuse color texture to write it back out. Diffuse color texture string. Okay, like this. So now we need the wax code. The idea is just to randomize the color texture for our agent here. If you look in the soldiers in the directory, it's in the reference files texture folder. You should have 4 different soldier variations. So we need to choose one for every agent. So they just vary in this number back here, 1, 2, 3, 4. So in the script, we need to find a random value for each agent for the number. So let's create a string attribute, which is called number. And let's use this ID attribute to fit a value between 1 and 4 because we have 4 different materials. So sealing that we get a integer value, and fit 0, 1 because we will do a random ID and need to fit this value between 0 and 1 between 1 and 4. So fit 0, 1 again and do random ID. Okay. And then we will between 0 and 4 because we have the ceiling expression and also want to get the 1. Okay, that should work. And now we need to set this diffuse color texture parameter. So diffuse color texture equals, and now I will copy the path from the shader here. Okay, let's do it like this. Go back in. I mean, you have to adjust it to your folder structure. Oops. That was not what I wanted. Let's get back. Sorry. Okay. And now put it here. Yeah. And now we will add the number which we randomly choose for every agent. And add the suffix with is just the PNG file extension. Okay. Like this, it should work. Now we have our snippet ready, and the last thing we need to do is here to assign it because we have a script from shop, but now we need to select the script, which is a random texture. And as I said, we need to do this data binding so it knows which attribute will be used for the randomization. So this is ID attributes as is fine. Now Houdini will select at render time a random texture for every agent. I mean, in this case, it's really easy because our agent just have one texture for the whole body, but you could also get variation for different parts of your body. So for the head, for example, or just for the jacket and so on. So let's jump back to the scene view. Here we are. Like I said, it's just visible via render time. And to check this, let's get a nice view here. Okay. And now you can use this really handy rendering feature in the viewport here. Just select it and let's see if it's working. Now Houdini automatically created a Mantra IPR render out for us. And as you can see now, yeah, it worked. Now we have different soldiers, one more with a whiter texture, this green one here, and they also have different skin tones. Yeah, that works very nice. So I guess our scene is ready for first rendering. As I already said, this was the last lesson in this course. I hope you could get more knowledge about the crowd features in Houdini, especially 15 with all the new ragdoll stuff. I mean, there are a lot more features to discover in the crowd because, as you already saw during the lessons, you can access everything in Houdini. In the geometry spreadsheet, you have all the attributes you have access to. You can even influence the bone position of every agent individually after the simulation. So there's way more stuff we could get into. But for now, that's it. And I'm really excited to see some more Ragdoll stuff on Vimeo. So all the best. And if you have any questions, feel free to get in contact with me. Bye bye.